Okay, hello everyone. Those who've been following previous live streams this afternoon, this is now not my day job. This is back to studying fundamental physics. And this is a continuation of yesterday's discussion about finding black holes. I think I reset my camera here, so for whatever good that does. So we're going to be looking at we're going to be continuing our discussion of black holes, and I think I will now just go to sharing that. Hold on one second. I'm confusing myself here. Let's see how this works. Great. Okay. Okay. I'm going to just go ahead and do this. Okay, we are talking about black holes here, and we're going to follow on from yesterday. So yesterday, we had looked at, we got rather distracted in what was supposed to be just a big black hole search, and started discussing all kinds of interesting things about space tunnels and so on. But we're going to return here. We're talking about space tunnels and such like, but we're going to return to the pure discussion of black holes. And so here we were looking at, so I want to make another version of this, and this is going to be black holes 03 for today. I'll make this bigger. Right, so the basic idea is we have a causal graph. Okay, so Jonathan has provided new code here. So should I just evaluate this code? Or do I need to evaluate the previous code first?
No. In fact, it probably makes, to prevent us getting confused, it might make more sense just to evaluate this new stuff.
Okay, all right, okay. So let's just go ahead and evaluate these things over here where people can see it. Okay, causally disconnected regions. So this is, you're going to explain what this is. So this is saying, highlight in this graph, this causally disconnected. So these are regions, I don't understand quite what's going on here.
Yeah, okay, so this is effectively the complement of a future light cone. So it's saying from vertex 2, which vertices cannot be reached. And so it's got a whole heuristic for determining, I mean, because obviously, this, as we were talking about yesterday, this is an undecidable problem in general, which requires knowing the whole of kind of future infinity. But it uses a heuristic to work out from vertex 2, which things seem to be unreachable.
Okay, so this is find the list of unreachable events from a given event, correct?
Right, exactly.
So in other words, i.e. events not in the future light cone of a given event. Okay, so something might not be in the future light cone if it was at the same simultaneity surface, so to speak.
Right, exactly. So the algorithm sort of has to account for some of that, which is why it's not, you'll notice it's not just showing everything that's on the right branch, it's only showing the late time ones, because those are the only ones it can kind of be confident about.
Are not what? So I mean, the question here is, what is the definition of a causally disconnected? What's the definition of sort of the black hole type thing?
Well, I mean, that part's easy. It's it's the complement of the vertex out component. The difficult part is determining the heuristic for figuring that out.
Well, wait a minute. Okay, so let's just define this thing. So an event A is causally disconnected from B.
Yeah, if the vertex out components are non-intersecting.
Right. If the future light cone of A and light cones of A and B do not intersect. Correct?
Right. That's a sufficient condition.
What's the necessary? What's different?
Let me try and figure that out. That's probably equivalent.
Okay, so let's look at the contrapositive or whatever of this. If the light cones do intersect, then it means they are causally. It doesn't mean those two events are causally connected, does it? No.
I mean, this is where it gets a little bit tricky to define exactly what you mean by causally connected. I mean, strictly speaking, causally connected means there is a path in the causal graph.
Right.
From
so
one to the other.
But causally connected. Let's be clear. Causally connected means because A and B are causally connected. A is causally connected to B. Means there is a path from A to B in the causal graph.
Right, but what we actually care about is which things will be in causal contact. So for the black hole case, the thing you have to be able to do in order to compensate for these horizon structures is you have to be able to say, okay, we have some event in the causal graph, and we want to determine, are there any events at the latest time step that do not exist in the vertex out component of that event, i.e. that do not exist in the future light cone?
Say that again. Wait a minute. What? I lost that for a second.
So to determine the asymmetric event horizon case, you have to start from a given event and determine which events on the latest time step do not exist in the out component of that event.
On the latest time step do not exist in the out component. So in other words, you could never get back. I mean, look, if we think about this, okay, one of the confusions is an event horizon. The normal notion of an event horizon is it's something that exists in space. We don't usually discuss event horizons as a function of time. Right? The normal interpretation of an event horizon is, I mean, and clearly that's not in fact correct, because a black hole might, if we lived around some star that might turn into a black hole, it isn't a black hole now, but it might be a black hole in the future. So what exactly is, when we talk about an event horizon, okay, remind me, in the Penrose diagrams and all that kind of thing, where we see an event horizon forming, what does that look like? Can we look at that?
Yeah, I mean,
am I asking the right question?
I'm not sure I agree with the premise. I mean, the definition of an event horizon definitely does involve time, right? The definition is the region beyond which it's impossible for null rays to. It's impossible to.
I've got a whole collection of Penrose diagrams here. Pick out one that we think is a relevant one for discussing what we're discussing.
Right. So I would say that an event horizon is a structure in space-time. Naturally, you can foliate it into surfaces.
Yeah,
in space.
I agree.
But it's,
all right,
it's
so show me that
structured
in one of
in
these
space-time.
diagrams. Could you pick one of these? What would you like to pick here?
Well, I mean, the first one is a good example.
All right, okay. We're picking the first one. Oh dear, we've got. Okay. Well, let's see. Penrose diagram of a Schwarzschild black hole here.
Right. So in the first one, you have there the horizon, right, where it sets the horizon.
Okay, so this thing, we're saying, oh gosh, this has time going up, which is kind of annoying. This is outrageous what I'm about to do, but it will make me less confused. Maybe. Okay, so what's happening here? So this is the black hole.
Yeah, so the horizon exists at 45 degrees, which means, as I say, that it's impossible for null rays to escape to future infinity, i.e. to get, intuitively to get infinitely far away from the black hole, infinitely far into the future.
Right, but so let's understand this diagram translated into our causal graph.
Yeah, that's exactly what I'm talking about. So the definition of future null infinity is the limit of the out component of the event. So what you're trying to determine is which of the events at the latest time step and do not exist in the out component of a given event at a previous time step.
Okay, wait a minute. I'm too slow here. Okay, so let's take this picture, okay, and imagine that we just use this as a template on top of our causal graph. Okay, there is a node in our causal graph here, and its future, because this is the future light cone of that event there, is all in the black hole, right?
Yes. So you can't have causal edges going beyond 45 degrees in the conformal diagram.
Right. But so what you're saying is that nothing
therefore,
from that
everything
node,
that's on the outside of,
yeah,
everything that's on the outside of that horizon, which is which you'd have to go at an angle steeper than 45 degrees to reach, will not exist in the out components of that vertex.
I get it. Okay, so let's just walk through this again for me very slowly. Okay, so this node here, its out component lives down here. And the point is that the out component of this cannot include something that, here's what's confusing to me, okay? The out component of a node here could intersect with the out component of the node here. Because
yes, exactly. That's the point I was making about the asymmetric event horizons. That's why we have to consider the cosmic and black hole cases separately.
Okay, all right. So let's just walk through this again, please.
In the cosmic case, the two events that lie on either side of the event horizon, their future light cones will not intersect, which is why I was saying it was a sufficient condition, but not a necessary one.
Jonathan, you're speaking too quickly.
Okay, sorry.
Maybe I'm just dense today, but slow down a second, okay?
So, you have a cosmic event horizon.
This isn't the cosmic event horizon. This
no, exactly. So in the cosmic event horizon case, as in the one above, the thing is symmetric. So because there's disconnection on both sides, you know that if you have two events, one on each side of the horizon, and you compute their out components, they're guaranteed to be non-intersecting.
Yes, I realize that. I mean, it'd be good to get a Penrose diagram for that case.
We can get one. Hang on.
Okay, so
then to deal with the black hole case, what you're really asking is, as I say, are there any events at future null infinity that do not exist in the out component of a given vertex? And if the answer is yes, then we know that that vertex lies inside an event horizon, a black hole event horizon.
Hold on a minute. So
we look at future null infinity. Future null infinity is the whole bottom of that diagram.
I realize that. For this, future null infinity for that node is
no. Future null infinity is a property of the global spacetime. Future null infinity is the whole bottom layer of the causal graph. That, as I say, all of the events at the last time step. And then the question is, do those events lie in the vertex out component of a given vertex? If that vertex is outside an event horizon,
I understand.
Then the answer is yes.
The black hole test. No. Okay, black hole test. Does every quotes final event lie in the future light cone of any given event?
Right, and so if you look at my code, that's effectively what it's doing, albeit very inefficiently.
Okay, so more specifically, for all events, of lie in the future light cone of all events, basically. That's really the question. Do there exist events that for which? Okay, so that's effectively what your code is doing here. This is saying.
Yeah, so in practice, what it's actually doing is it's computing, it's looking at everything up to 1/2 of the time steps. That would be up to step 2 in this case.
Yeah.
And then it looks up to the full time step, and it asks, are there any events at step 4, in this case, that are not reachable from the events that were produced at step 2? And so that's kind of, doubling is our finite way of approximating future null infinity, which is of course very crude,
let's write that down more carefully. So I mean, what you're saying here is this is asking for these possible nodes, if there were no black holes in evidence, every node, every element of this list would have the same right-hand side.
Well, actually, no, there wouldn't be any elements of this list, right? So because the right-hand sides are showing you which can't be reached. So, okay, if you go to the rule and you change BAAB to BAB, you should get an empty list. Because I think that space-time has no event horizons.
BAB?
The right-hand side of the first rule, you change that to, because basically the reason it's producing event horizons is because that's a superluminal expansion. But if we remove it, you no longer have superluminal expansion.
Okay. Hold on. So these are, okay. So every element, there would be no, I see, there would be no unreachable elements, i.e. this list of disconnected regions would be empty. Okay, so what this means is, what the list is, it's basically something of the form node and then list of unreachable, list of nodes, list of final nodes unreachable from this node.
Right. And so, right. So one thing we can discuss is is if we can construct a better heuristic than the one I lazily came up with.
Okay, fine. But let's first of all just look at this question. Okay, so from a given node, and so currently looking at nodes at step t and at what nodes at step 2t are unreachable.
Right.
So I claim that we definitely need a version of that function in which we have a t0 and a t1 or a t final.
Oh, yeah, okay, sure.
Can I rewrite this? I mean, there's this
Yeah, I mean it's trivial code. We can, yeah.
Okay, all right. So let's go. So I think that will be a little bit clearer. So this is okay. So you say initial condition, then we say, I think we want a t test. Well, why don't we just say t initial, ti and tf? Okay, so what do we want to do here? So this is, just tell me where to do this.
So that's the final. So step. Okay, well, first of all, hang on. I'll tell you what. There's actually an optimization I want to make as well. So I can just write this and I'll send it back.
Okay. All right. Fine.
All right.
Okay. But. All right. Okay. Okay. While I'm at it, should I be understanding these other Penrose diagrams for these other cases? What is the extended Schwarzschild geometry? What is the point?
So that's the second one.
No, I understand. But what's the? This is simply another solution to Einstein's equations, correct?
So that's the full continuation of the Schwarzschild solution, which has this one hole inside, say, to another parallel universe. So the diamond. So to understand these diagrams, it's better to start with the diagram of Minkowski itself, which is like one of these diamonds, in which you would have the four boundaries, the two past null infinities and the two future null infinities. So when we have a black hole, then we have the structure of the first one, in which the singularity becomes space-like. This is what we were discussing the other day, that the singularity is more like an instant in time in which everything disappears. You are going to hit it no matter what. And that's why the singularity is drawn horizontally.
Right.
So everything that enters the horizon, which is the tilted line, is trapped inside because it can only evolve towards the singularity.
Sure. But I'm asking, in the normal Schwarzschild solution, so if I just solve the Einstein equations on a manifold that has a hole in it, for example, then then both of these are valid solutions to the Einstein equations, correct?
Yes, you can consider the second one like the continuation, the analytic continuation of the first one. Like the first one is the one that contains the reasonable physics, and the other one is just the continuation.
With different boundary conditions, effectively.
Yes, if you want.
I just sent the code, and I updated it to it also deals with the Wolfram model case in case we want to do that.
We definitely do. All right. Are there more Penrose diagrams that I should look at just to understand more about? I mean, in other words, well, we need the Penrose diagram for a cosmological singularity, cosmic singularity.
Right, and the other one which is important is the one of a process of the physical process, because these solutions have the problem that the black hole was always there, and so it's not the process of formation.
Right, that was what I wanted to see. Right, that was exactly what I wanted to see. So can we find a Penrose diagram for the actual physical case?
Yes, if you go back to that big list that you had at the beginning, probably it's one of those.
Pick your...
Yes, so it will be go up, or for example, I see that 1, 2. This is one which has like a gray area.
That one there?
Which one are you? So for example, this one which is to the left of that one.
That one there?
That one, yes. Right, so there you have
time going upwards. It's so freaking confusing.
It's the standard. To me, the other one was very confusing. So there you have like the surface of the star, and you see how at some point it's yes, at some point the horizon, the event horizon appears, which is this red line, and then the star crosses the horizon and collapses to the singularity.
As opposed to this case, I don't see the difference. I don't understand the difference between...
So, for example, imagine that there was no black hole in the second one. Then the diamond would have a pointy end in the future.
Here.
Like,
yes,
exactly.
It would be a triangle.
Exactly, yes. So the fact that even that the black hole appeared created the event horizon, which is a surface that appears from the center and grows towards infinity. And then the singularity is inside, and it's space-like. So you might have a situation in which there is a singularity which is vertical. This is the time-like singularity that we were discussing the other day, that is forbidden by the constant censorship.
Right.
And so
but which exists, for example, here in this Kerr black hole.
Exactly.
Okay. It's amazing when you just solve random equations and you can, and there are lots of weird things consistent with those equations. It's just so much more confusing than when you have these evolution rules. Anyway, never mind. That's just a bitch for not.
So what the simulations say is that if you try to create numerically this time-like singularity, it's very unstable. And so physically, it's not going to be there. And internally, as we were discussing the other day, the dynamics is very chaotic and it's going to be very different. So it's going to look more like this one we see on the left, or have null singularities, but not time-like.
Okay, here's quite a nice picture of a cosmic event horizon, figure 1 of this paper. So that R equals L there would be a cosmic event horizon.
And is this the same form of diagram? I don't quite understand this.
This is a Kruskal diagram, which is not, it's similar.
This is not compactified.
Right. The problem with Penrose diagrams is that their coordinate system is not well suited for describing cosmic event horizons.
Okay. That says it's a Penrose diagram for a de Sitter bubble.
Right.
Can you explain this picture?
Let me understand what it's saying. I'm not sure what this is. Jose, do you know?
Well, this is like similar to what we had before with the two copies of the exterior universe and then the black hole area in.
Okay, but that's again not, we don't quite understand whether this is like the okay. Fine. We don't understand quite whether that's like whether that's a cosmological event horizon or something different. Okay, let's go back here. So this is now, let's just code.
I don't know what the Kasner de Sitter bubble nucleation is.
Well, I assume Kasner is like Kasner universe, isn't that one?
Yeah. So really the Kasner metric, but coupled to some de Sitter metric, and then there's a bubble nucleation. I don't know.
All right, we got this code here. Okay, so now we've got, again, you've got get causally disconnected regions, right? Yes. Okay.
Yep.
Initial
but
time,
now with initial and final times.
Okay, fine. So let's do this here. So now let's see what this looks like with initial time 1, final time 4, for example. Okay, why am I not seeing all nodes here? Oh, maybe I need initial time 0, perhaps?
Wait, what?
Why is there just
there's only
2?
one event at time step 1.
But why is it labeled 2 then?
Because it's seeing what new events got produced. Okay, I'm not sure whether substitution system causal graph includes initialization events or not.
Yeah, I see. Okay, fine. But so let's take this and let's do this and let's do the graph here where we have vertex labels arrow true, automatic. Okay, I am already confused here.
Oh no, so that does make sense. Yeah, so 1 is causally connected to everything.
I see. 1 is causally connected, but 2 now
is disconnected from everything on the right, which in this case includes 26, 27, etc.
So wait a minute. Why we just said 4 steps here? So why is it showing me the ones from 2 different sets of steps?
It's not.
Oh, because
there's a causal graph.
Depth. Yeah, there's certain depth in the causal graph. My layering of this causal graph is purely coincidental.
Yeah, exactly.
It's not the shortest. Okay, so that is showing. Okay, so in this is showing what looks like a cosmic event horizon here. Is that correct?
Yep, looks like it.
Okay, so let's do our test for. I don't understand. Oh, I see. 2 goes to that side and 2 didn't go to this side here. All right, so let's keep going to make sure we understand what's happening here. So if I go to step 2 there, and let's say I insist on step 5 here. Okay, then what I should get is 2, 4, 6, 8. What happened to, okay, 3 is connected to everything. Why is 5 not showing up here?
I don't know. I'm not sure what time step 5 appears on.
Well, time step. Oh, it's time step. Is it time step 1?
Wait, hang on, wait. No, 5 does appear there. 2, 4, 5, 6, 7, 8.
Oh, yeah. Right. Okay. All right. So then this is all right. So let's this probably could have been an association, but let's go ahead and ask. Okay. So first question is, what's the first of this? Okay, that's 2, 4, 5, 6, 7, 8, 9. 2, 4, 5. Okay, so these are the left-hand sides are the things whose future light cones are not complete, so to speak. The LHS nodes, events, are ones, does that have a name in general relativity? Whose future light cones are not complete. Does that have a name?
What do you mean? Not
Well,
complete?
I mean, this is just referring to, in general relativity, is there a name for an event, for a space-time point whose future light cone includes the whole universe? Because that's what this is saying. Those events are not, so in other words, any event like 1, for example, doesn't appear here because its future is the whole universe, right?
Mm-hmm.
Right, but and by whole universe you mean future null infinity. So I'm confused by the question because I don't know what the difference is between what you're asking and the definition of an event horizon.
There isn't. I mean, it's just saying, I'm just asking, is there a complement of saying that there isn't an event? It's just, there is no event horizon. Okay, so,
right.
Okay, so here, let's make essentially what we want is a Venn diagram of these, basically, right?
Right.
Essentially what we're asking for is, so is there a way of drawing that Venn diagram, I wonder? Is that how we want to do it? I mean, what we want is the intersections, the relative intersections of these things. So that represents a graph that these things here, if there is an intersection, well, so one question, okay, so
I'm not sure I understand.
Okay, what is the, quotes, causal connection graph of nodes, 2, 4, 5, 6, 8, okay?
And by causal connection graph, you mean?
Well, I don't know what I mean. I mean the thing that is going to turn into the thing that we can look at properties of to find out if we have a black hole event horizon, a cosmological event horizon, or something different. Okay, so for example, the causal connection graph says that 2 has certain nodes. Look, 2 might completely overlap with 4. See what I'm saying? So 2 and 4 have the same future light cone.
Except for 4.
Fine.
Yeah.
Right, but but in particular, by the time we get to these final states, the final time step, future light cones of 2 and 4 are identical.
Yeah, right.
Okay, so there's an equivalence class here of things whose future light cones are identical. So what are the cases? Case 1, future light cone of A and B is identical, or final light cone. I'll call it final light cone, okay? So I'm saying final, yeah, let's say final light cone. It's kind of a weird thing to say, but you get what I'm saying, right?
Right, a future null set.
Okay, final null set of A and B are identical. That's one case. Okay. Case 2, final null set of A contains final null set of B. Okay, and the other one is that they're intersecting in some way, right?
Mm-hmm.
So for every AB, we have these relations. They're either identical, or they have a containment, or they're disjoint.
Okay.
Well, no. The next case is they intersect, and the next case is they're disjoint. Okay, what is a good graphical way to represent those different possibilities? So do we want to represent them? I mean, in some sense, a Venn diagram would be a good way to represent this. Do you agree?
Sure.
But what else? We need a graphical representation. It's going to get significantly more complicated than this. If these are the cases, what is the right way for us to represent this? Right? Because we don't want to have to look at this right-hand side. We want to be able to just look at a signature, basically, of these events at a given step and what is their future connectivity. See what I'm saying?
Yeah.
Okay, so that's what I'm asking is what's a good way to visualize that? And I'm claiming a Venn diagram, but is there a graph version of a Venn diagram that would be equivalent, so to speak?
Well, I mean, why not just plot the set relations as a graph? Set containment defines a partial order, so we can define it as a directed graph.
What about intersection? That's not, oh, I see. Intersection, that's not containment. That's the problem. That's a different type of edge. Right, containment is fine.
Yeah, so cases 1, 2, and 4 we can definitely represent.
Yes, that's right. So case 3 is the tricky one.
Well, case 3 is the case where both A and B connects to some common vertex C.
Hold on, let me just look up something. Do we have a Venn diagram? Oh, Venn graph plot.
But why not represent it as a graph?
I guess we could add a fake vertex representing intersection.
What does this?
No, but my point is, if they're intersecting, if A and B have intersecting future null sets, then there is an event that's in their future whose future null set is that intersection, I think.
Oh, right, that is a fake vertex.
Yeah, right. So yeah, exactly. But is that a fake vertex? Or I mean,
It's a fake in a sense that it's not on this level.
Right,
but
so the intersection.
It doesn't have to be specific to a level. I mean, I think this is right. That the signature of intersection is just A goes to C, B goes to C.
Fine. Okay, fine. So that's A goes to C, A goes to some X, and B goes to some X. And that X then has what property with respect to these other things? That's another node. See, I'm very confused by this because what we're saying is we've got A, B, which are at a particular level, right? That's your T sub I level.
Right.
Make sense?
Right.
But the intersection is calling for a bridge, so to speak, at another value of T.
Right.
Well,
that's why I'm saying it's fake. But if you color this vertex differently, for example, and don't label it, it might be clear enough as visualization.
Well, the other thing we can do is just have an edge between those two things. It's a different kind of edge, tagging that edge. Let's try doing that with a tagged edge for the intersection. Okay, so these are partial order edges, and that one is okay. So let's write the function that basically makes the and I don't know how it's related to this. This looks like a very similar.
Maybe I'm slow. I still don't understand. Why are we constraining this only at the same time step? That's not the case you were describing before, where you were talking about future null sets of 2 and 4, which are different.
Because your function, Jonathan, has two time steps in it: T sub I, T sub F.
Yep.
And what we're asking is, we don't care about T sub F except as an indicator.
Yeah.
Right. T sub I, we're asking the question, given the set of events at time step T sub I, what are their relative causal connectivities?
Yes, no, I understand that.
Okay, so what I'm saying is that to say that they have an intersecting future null set, intersecting final null set, is to say, as you're saying, and correctly, I think, that there exists a future, a time-like connected or null-like connected vertex X that is in both of their futures.
Yes. I don't dispute any of this.
No, right. I mean, that's right. Look, it's just
so I ask again.
Matter
so why do these have to be at the same time step when the problem as posed does not require that?
Why do which have to be at the same time step?
The claim is that this vertex X is fake in inverted commas because it exists at a future time step, but vertex 4 exists at a future time step to vertex 2, and we're not claiming that that's fake. So why are we making the assumption that the vertices that appear in this graph have to all exist at the same time step?
Okay, we're not, but I think it's going to be clearer. Why don't we do this? Why don't we just have the intersect case be a differently indicated edge, okay, for now, rather than creating a new vertex?
But we're not creating a new vertex. That vertex is there.
If we include all of the vertices, wouldn't we just get the causal graph back?
Yes. Yes. What we're trying to indicate is we're taking a slice. We're taking a space-like hypersurface, basically. T sub I is a space-like hypersurface, and we're asking on that space-like hypersurface, what will be the future mixing of the future, evolutions of the things on that space-like hypersurface.
I understand all of this, but let me ask again. So if we go back up to the graph you showed earlier, if we scroll up, right? So vertices 2 and 4 exist at time step 2, but there is a time-like edge separating them.
I understand.
So this is no different to the case of A is connected to X, B is connected to X.
Okay, the point that I'm making, Jonathan, is this: the set of vertices whose causal connectivity we are discussing is the set of vertices that exist on some space-like slice. That's what I'm saying.
Yes, like 2 and 4, even though they exist.
I realize that, but what I'm saying is let's not confuse it by throwing into, we can pick another space-like slice and we can ask now, at this state of the world, what are the event horizon structures like? But let's not confuse it by adding in to the description of where the event horizons are or where things are going to be causally connected in the future. Let's just try and make this visualization. We can then decide we don't need to look at the future intersection thing. We just need to find out, because we can just purely from what your function returns, we have these cases. So we simply want to work out for every pair here, right? We're going to work out for every one of these. So let's take this thing here and let's find, compute intersections basically, or compute intersection status. Compute intersection statuses. Very bizarre concept, okay? So of this thing, which I argue would probably be better as an association, but it doesn't really matter, okay? Of disconnected regions, okay? That's going to compute this for these disconnected regions. So for every, well, actually, no. Intersection status of a given pair of list 1, list 2. Or intersection rule for these two things. Okay, so I want to make that so the different cases. So it is a which of so if they're not intersecting Q, list 1, list 2. I hate witches. It would have been good in the whatever. Never mind.
I don't
Forget that.
use conditions and multiple definitions for this.
That's a better idea, yes. Yes, thank you. A much better idea. Otherwise, I'm going to get myself in trouble for some Wiccan discrimination thing of hating witches. Okay. Okay, not intersecting is this, right? That case, correct? That's what we're going to build from this. If, on the other hand, subset Q, right? Subset Q, list 1, list 2, then the subset Q is not a proper subset, right? Am I making sense?
That's a good question. I don't know.
Okay, well, let's find that out. So let's say S1 arrow this, S2.
Yeah, non-strict.
Okay, S2 arrow this. Okay, so that one is this. Okay, now S1 arrow this, S2 arrow this, subset Q. So if they're non-strict, if list 1 is, so then list 1, which way? Okay, fine. So I claim that becomes this. That becomes that directed edge. Do you agree? Right? I mean, you see what I'm doing here, yes? Jonathan, Max?
Yeah, makes sense.
Of course.
Okay, list 2, list 1. S2, S1. Okay, so the final case then is that they are, so the final case.
Intersection, but not subsets of each other.
Right. Intersecting Q and not subset Q and not subset Q list 2, list 1. Moment, what if they're equal?
Then there will be subset of itself. And we will
Or if they're
have
equal,
edge
then it's
going
a
both
two-way
directions.
subset relation, right? Then it's
Right.
a two-way
It's an
diagram.
undirected
Okay.
edge.
Okay, so in this case, then, this is the dotted line case, basically, right? How do we indicate that? Do we put a tag on this edge, or what do? We say tagged edge? Is there such a thing? How do we do this?
Can you make it undirected edge and then style them differently? I don't know if it will work or not.
Okay, so now what we do is up here, we get this. And what we're going to do is we're going to say outer, or can we just do a tuples, comma 2? I can't remember. Tuples of this thing.
I'm not sure if that's the right function.
Which function? This function here.
You want the causally connected regions, not the causally disconnected ones. Don't you?
Yes.
Right. So I'm sending you a new notebook with those functions.
Okay.
There you go.
Okay, causally connected regions here. Okay. Really? Is this what I want? Well, okay. I'm not quite
That was the problem as
understanding.
you described it.
Oh, you
Maybe I
want a
misunderstood.
set of reachable points from each of them.
Okay, so it's this, flatten that, and graph that. Okay, so what's this showing us?
But I think it might have a problem. If they are identical, it will actually call both of those functions.
Oh yeah, that's true. You're going to be screwed by evaluation order
Why?
because whichever evaluates first, that will be the one that evaluates.
So you're saying
It's the issue,
we'll never reach this case.
right? Because we're doing conditional evaluation.
No, it will reach the fourth case. It wouldn't reach. If both the second and third one are true, it will only reach one of them.
Okay, but okay, look, what we're trying to do is we're trying to get a map for a given T sub I of what the future connectivity of all these things is going to be. So what we should see, the thing I'm confused by is why are we not seeing every node? Oh, we are 2, 3, 4, 5, 6. Okay, fine.
I think we all.
So this should be strict subset Q, basically.
Yeah, subset Q and not list 1 equals list 2.
Yeah.
Okay, all right.
And then add another evaluation point.
Okay, so here I want this and not. Let's just do it the other way around. Subset Q. Is there a strict subset Q?
Not that I know.
Okay, so now we want intersection rule. So this is the equality case.
Yeah.
Intersecting and not subset and not subset. No, that's the pure intersection case.
Well, yeah, we need a new case for equality.
Right. So we need an equality case, which is that the sort of list 1 triple equals the sort of list 2. And then that one becomes the double directed edge. Okay, let's try all of those. That's that. So this is the same thing again.
Well, no, because now it deals with the equality case, so we have 2 loops rather than 1 loops, amongst other things.
So what do we conclude from this? We conclude that, so if we were to take this and say simple graph of this, for example, what's that going to do?
Right. So we can infer from this immediately that, for instance, 5 and 6 are causally disconnected.
5 and 6. Okay, so how do we draw that in this graph somehow? How do we deduce that easily from this graph? How do we indicate the event horizon? What is the graph theoretic way of discovering the event horizon?
Well, all non-adjacent vertices.
Okay, so what's the difference then between so you're saying anything that isn't a complete graph. Don't we want the complement of this graph? Isn't that more useful?
Yeah, I agree, but that's not the problem you described. I agree. I think seeing the causal disconnection is in many ways more useful.
Hold on, in the case of black hole, wouldn't it be that we can go one way but not the other way?
Yes, in this graph. Right, this is the causal connection graph. And this causal connection graph is saying you can go from 1 to 8, but you can't get back from 8 to 1. Right?
So we need to find a subgraph which doesn't have any outgoing edges from it.
Yes, that's a black hole. Right. So for example, 8 here is something that has an event horizon relative to 1. So in this graph,
Well, 8 is a black hole in itself.
yes, but it's okay, right. But so the question then is, what is the subgraph in which there is connection between the nodes, but you can separate this into subgraphs? So isn't there some standard community-like mechanism for describing this question of whether there is a subgraph, whether it separates out? Francisco on our live stream is pointing out there's a mistake in line 13, line 8. Should be connected with the range of intersection. I'm not sure. I think we probably fixed this. Okay, so again, let's figure out. Okay, so first question is, let me just write the thing that says this thing here, right, is otherwise known as basically, this is our causal connection graph, which is what we tried to do before. Causal connection graph of our rule init TI TF is otherwise known as this thing here. It's kind of goofy. Let me just compute this separately. Okay, so that is so here we could say causal connection graph of this thing here. And I don't know whether simple graph is what we always want to apply. Am I making sense? Is simple graph always okay to use?
I guess for our purposes it is.
Why are there multiple edges? I don't understand why there would ever be multiple edges here. The outer...
Oh, actually it's a good point, because we do need... That means they're equal.
When there are multiple edges? No. When there's a back and forth edge, it means they're equal. See, the back and forth edge, it means it's equal. Why are there multiple edges from that node to this node here?
Oh, is it because each tuple appears twice? We probably don't want that.
No, it's the tuple each way round. It's ij and ji, which is
right, and we don't really want that.
Yes, we do want that. We absolutely want that. they're not symmetric. If A is connected to B, it doesn't mean that B is connected to A.
But the way we compute the result from it is symmetric. In that we
No, it's not.
produce an edge in both cases because we have the
then we
subset
got this
function
wrong.
going
We got
both
this
ways.
wrong. We're saying subset, because we're going to do it all ways round, we actually don't want this case, right? Am I making sense? This case should be the null list.
Oh, sure, we can do this way too.
Well, alternatively, just say simple graph. That's fine. Either way, does it work both ways? Do you see what I'm asking?
Not quite.
Okay, so look, this is going to generate, for A and B, if A is a subset of B, then this will generate a directed edge from B to A. Right? We're then going to test it a second time. It's going to have a second entry in the tuples, and it's going to get the same edge.
Yeah, so it seems to me we just shouldn't do each tuple multiple times.
Well, whatever. I mean, we could do that, but I don't see the point. I think what we want to do is just say simple graph of the whole thing.
So I'm wondering what simple graph would do if we have both undirected and directed edges.
I think it doesn't. Well, we can look it up, but I think simple graph will just leave. You mean if there's both an undirected and a directed edge between two nodes? I don't think that can happen.
Yeah, that can't happen. Yeah,
Right.
probably.
So in this diagram, what we're seeing is, so let's take a look at that diagram there. And we're asking, okay, so let's look at what that diagram does if we go one more step, for example. Okay. So that will probably be stable at that point. Okay, so we can have confidence that that is the correct diagram. So for example, if we go to step 3 here, okay, so we're getting a more complicated thing, but I think the structure is becoming a little clearer.
So I think what we should do here is to find strongly connected components and then make a plot of those, which would be a tree, and it would essentially show us where the black holes are.
Okay, that makes sense. Okay, so fine. So let's take this graph here. Okay, so this graph is already giving us an indication of what's going on, which is roughly that there is a region here where everything is connected to everything, roughly. I mean, this is like, this seems to be some kind of cosmological event horizon, sort of. Do you agree? But
yeah, that's what it is. It even looks like a Penrose diagram.
Okay, but so let's try to understand how to compute. So you're saying we want these strongly connected components, which are exactly the things which have two-way connections between them, right?
Yeah.
Okay, so let's take this guy here, and let's say, give us the strongly connected components of this. What is it called?
I
Strong
think
components,
it's
isn't it?
connected components because
Say
it's
again?
strong by default.
Okay. Really? Is this right? Okay, so let's look here, the graph. Okay, so this is claiming 1, 3 are a strongly connected component, 5, 9 are a strongly connected component. So this is broken into many strongly connected components. So what is Max's proposal here?
To represent each component with a single vertex.
Okay, and then do what?
And make a tree out of them according to how they're connected to each other.
Why is it a tree as opposed to a graph?
Well, because if there is a loop, it means they're in the same component because you can go to every node in any of them.
SWSH on our live stream is suggesting doing an outer complement, but I don't understand that. I don't understand that.
Yeah,
sorry,
so if within a single strongly connected component, you can go from every vertex to every other vertex.
Indeed. So
if
we
you
don't
have
want
a loop in a, well, if the graph of connected components have a loop in it, it means you can again go from each vertex to another one, which means it's actually one strongly connected component.
Yeah, so you're saying this thing here. Okay, so hold on. So basically what you're saying is compress every connected component to a single node.
Yes.
Okay. So how do we do that? Is there an easy way to do that? An easy graph theoretic operation that does that?
I mean, it's not hard to do manually, but it might be better way of doing it.
Well, we could just take one representative of every connected component and then we'd be done.
Oh, exactly.
Okay, so then essentially what we're doing here is we just say subgraph of this thing here, comma, first slash at those connected components.
Yeah, but you have to recompute the connectivity.
Why?
Because there might not be an edge from that component to another one.
You mean that
you might have to go through other vertices.
That member of that component, basically.
Yeah.
Okay, fine. So you're saying we have to compute from each. So what are you suggesting here?
Hold on. Isn't there a way you can merge vertices into one?
I thought there was.
Why don't we just do a slash dot of all vertices that aren't the first vertex to the first vertex?
Oh, that's
the representation of the graph. Yeah, that would work.
It seems like the easiest way to
let's make an equivalence class. So that basically what we're doing is we're replacing every vertex with the first vertex. But let's just look up whether there is a way to do this by.
There is. I looked a while ago because I had to solve this problem in a different context. As far as I know, there's no way to merge vertices without just doing slash dot.
Okay.
What does vertex contract do, if it exists? It doesn't exist.
It doesn't exist. Edge contract exists.
Vertex contract does exist.
Does it? It's not. Is it documented?
Well, it has a user's message.
Yes, it does exist.
Oh, hang
on. This appears to do exactly the right thing. This appears to do exactly what we want. So this is vertex contract.
So you just do vertex contract of graph, comma, connected components of it.
Right. Yeah, exactly. Contracts a collection of vertices into a single vertex of the graph G.
Wait, don't you want to map vertex contract over connected components?
No. Look at the usage. It says contract several collections of vertices. Oh, maybe all together?
Well, if they're all together, why wouldn't they be in the same list?
Okay, creates a new graph by removing all edges between Vi and Vj and merging them into a single vertex V1. Why doesn't it have an example of something with multiple? No, there it does. Oh, this is using fold. It's documented to use, okay. It's documented to use these things, but it isn't. No, we can certainly use fold, but I'm going to send mail to Charles here. Given the documentation of multiple lists,
yeah, looks like it doesn't work correctly.
Okay, but clearly we can make fold do this. Of the original graph, here, comma, connected components. Okay. All right, cool. Okay, so that is then a skeleton of that space-like surface, right? That's showing us. Okay, so let's just.
Oh, that's a nested collection of black holes.
Which is generically what a cosmic event horizon will be, right?
All right. Okay. So fine. So let's
If
just
you
write.
have a superluminally expanding universe, locally it'll always look like a.
Yeah. Right. A collection of black holes. Right. Okay. So this is causal connection graph, and so this is what is this? This is causal connection summary graph.
Causal connection DAG.
Let's just call it causal connection summary, and that is rule init TI-TF, which is otherwise known as with G equals causal connection graph of rule init TI-TF, and then we need the fold of that over G comma connected components of G. Okay, so causal connection summary. So then the end result of this would be, we could say causal connection summary of this thing here. And that's going to give us this graph here. So now we can say, let's do the causal connection summary at level 2. And then let's do the causal connection summary at level 3 and level 4. Okay, so that's showing, what is that showing? At level 4, it's breaking into, so let's just see whether we heated to constant weight, so to speak, here, and we did. Right, so we probably could do a nest. We probably could do something where we test whether we've reached the final state. Okay, interpret this picture. So you're saying there's just a nested collection of black holes forming.
Right. Each node is a black hole.
Okay. All right. So let's go back then, and let's do this for all rules. Okay.
But I don't think that's a useful way to think about it, because as I say, that doesn't make the appropriate distinction between cosmic and black hole cases.
All right. Okay. Fine. Let's go back and look at the case that we were looking at here, where we were looking at. Here we go.
Right. So I mean, take for instance, the one on the bottom left there would be a good one to.
All right. Let's try to take all rules of this type. Okay. AABA was our thing here, and so these we want. All right. Let's do this. Let's take this rule AABA. Let's say 5 steps. And causal connection summary of this thing, let's say 7 steps or something. I don't know what we could pick. And let's say 2 steps here, 3 steps. What do you want? 3 steps. Hash AABA. And let's just, we can just do this. And now let's say, resource function of parallel map monitored. Okay, this over the enumeration of those rules. All right, let me widen this out because we're going to get a big output here. All right, here we go. So this should be generating, I better put a time constraint here. Five seconds. Okay, here goes. Okay, launch the machines. Since we do want a factor of 100 faster output. It's really annoying. It takes so long. I complain about this every single time that it takes so long to launch these machines. Splat. Okay, I wonder what happened to that machine. Okay, let's see what's happening here. Okay, so these are mostly trivial. Come on. So what this means, what does this mean here?
What was your initial time?
What's that?
What was your initial time?
I think it was 2. No, it was 3. So 1, 2, 3.
Well, we have no idea how many events are at level 3.
We have to look at this graph, right? But I mean, so let's see whether there's anything non-trivial that happens here. Okay, what about this guy here? So that one there seems to be, and that one there seems to be forming what you might think of as a, I mean, notice that we have no undirected edges anywhere here. Okay, that one is very simple to understand. Right?
Yeah.
Well, are we generating the correct results here?
Well, as I say, I think we should analyze that black hole result more closely because that doesn't look correct.
Okay, yeah, let's just look through here. Okay, let's go back up. Which one were you saying?
The black hole, the one non-trivial asymmetric event horizon case. That one.
This one here?
No, down. Well, actually, I mean, there's one there. Yeah, that one.
This one here?
No. One up and to your right. The event horizon case.
One up.
And to the right.
This one here?
Yeah. I mean, there are several.
Why isn't it correct?
It's what we now want to analyze is the causal disconnection graph, which is what's going to give us the indication of the black hole.
Doesn't this give us indication of black hole? Because you can go to the right, but not to the left.
Right. I mean, isn't that exactly what this is? That's saying that there is causal connectivity between the first connected component, the universe. Each dot here is a connected part of the universe.
Okay.
And I would think if at level 2 we were already disconnected, we already had 2 disconnected universes, like here. Oh yeah, there we go. Yeah, it's hard to see them, but there are the 2 disconnected universes, right, that occur in this case. Right, they're those 2 dots.
Okay. So are there any non-event horizon cases then?
Yeah, this one here. It has 1 dot.
Okay. Which
Another
is
thing
wrong.
that has only 1 dot. So this one here, what is this here?
Yeah, so that's not a non-event horizon case. That's why I'm confused.
This one has
no. The one with 1 dot is not a non-event horizon case.
Well, I think the issue is the connected components here. You're claiming that that's the wrong result.
Yeah, well, I'm wondering what these results are because they don't seem to make sense to me. But maybe I'm just confused.
They're what we computed from your code, right? Unless we did something wrong. Okay, so
in that case, there was just 1 vertex on the 3rd level, wasn't it?
Yeah, that's what I'm wondering. Without knowing what levels the vertices are at, it's very hard to interpret what these
Okay,
mean.
so how do we indicate what levels the vertices are at? Do we draw a foliation, or what do we do?
Well, we could layer
could
by
just
step number.
highlight them.
Say that again.
Well, layer by step number 1, but we can also just highlight those vertices.
Which vertices?
The ones at the
On
level
this-
being considered.
Okay, fine.
Right.
Let's do it. Let's do that.
And
Let's
it
do
might
that.
be useful to label them as well.
Fine. Okay, let's do it. All right, so we're going to go here and we're going to say the vertices at that level correspond to taking this thing, and we'll compute for this. So this will say with G equals this. Is the first vertex vertex 1? Did you understand my question? Is the first vertex in the causal graph vertex 1? Do you know?
It's not my code. I assume so.
Okay. So we want the neighborhood graph, if I'm not mistaken. We want to, here, we want to say highlight graph of G comma neighborhood graph of G comma 1 comma, in this case, 3. Is that correct? Is that correct? Max, can you follow this? Is that correct?
Looks like it. Well, don't we just want to highlight level 3 only, not all of them?
How
Up
do I
to
do
3.
that? Okay, I do that by doing a complement, right?
Yeah.
So I'd say graph complement of level 3 minus level 2, correct?
I think it's a graph complement. Well,
What are you saying?
yeah, I'm not sure what graph complement does exactly.
Oh, graph difference.
Could just use vertex complement.
No, why don't we just say graph difference? Is that right?
Might be.
Can you look it up, please? I don't think it's correct. So you're suggesting that I say vertex complement here.
Well, I'm suggesting to get vertices from both of them and then do complement.
Well, then that's the out component, right? Is that correct?
Yeah.
What is it called? Vertex out component?
Yeah, I think so.
Okay, there we go. Okay, so that's showing the level 3 things. And then what you're suggesting is that we label both of these. Is that correct? We label both of these graphs. Is that correct?
Yes, but I'm not sure it does the right thing. Because if you look at the first example here, from wherever it takes them to produce a second graph,
I didn't understand. So
inside causal connection summary, it has a list of vertices which to use it for the second graph. So we should just use the same list of vertices to highlight.
I see, which are members, which are the representatives of the connected components. Right? It's not the full connected component. But I don't understand why there's a vertex 1 in here at all. Because that wasn't in T sub I. That shouldn't have been in the initial state there. Do you understand what I'm saying?
Yes, I don't think the label the same. Doesn't look like it.
Okay. Well, let's understand that. So
I'm not sure what
connection
happens.
summary.
when the
I'm
contract.
sorry?
So when you do vertex contract, I'm wondering which vertex does it
It says
keep?
V sub 1. It says the first vertex in the contraction list. That's
Okay.
the representative it's picking. Right? So you're saying, I mean, I think the code we had above, this code, this causal connection graph code, I believe is preserving the numbers, the vertex numbers here, correct?
Well, it should be, but then we wouldn't have vertex 1.
I'm sorry?
I mean, it should be, but then we wouldn't have vertex 1 on the bottom, so something's going wrong here.
No, I'm trying to understand. This one here, so let's take this case here, right? Okay, so this case here, we've got that causal connection graph. And now let's take this. Now, I mean, this is only labeling the oh, that's just labeling, sorry. That's just the causal. Okay, so that's this. Okay, we want this rule. Oh, sorry, we want this here. Okay, so that's labeling the nodes there. Okay. Right? Yes, understood?
Yeah.
Okay, so what should happen is that's the things at level 3, right? So the causal connection graph here, if we label it should contain the same, it doesn't, so something is wrong here, right? This contains 1 and 3, which are higher level up here, right? Not the things at level 3. This was supposed to contain only those things at level 3. Jonathan, I think.
Let's check how we select the vertices.
I'm sorry?
Let's check how we select the vertices in causal connection graph.
I know, it's Jonathan's code. So Jonathan, can you say?
Wait, causal connection graph is not my code. Get causally connected regions is my code.
Okay. All right. So let's look at causal connection graph here. But what was causal connection summary? That is summarizing this, having reduced it. So let's just look at the causal connection summary and see what it does. Okay, so that has
that still is
down to level 3, right? So that has vertices.
I think it takes up to level 3 instead of level 3 only.
Mm-hmm.
Yes, I agree. So let's figure that out. So this is causal connection graph. Okay, causally connected regions is getting only at level 3, or I don't understand that quite. Is this causally connected regions, the T sub I here is down to T sub I or specifically at T sub I?
Yeah, down to T sub I.
Okay, that's different from what we, okay, I understand. So then what we'll want to do here is to remove from this those nodes which are above level T sub I, correct?
Above level Wait, what?
Above level T sub I, prior to level T sub I, we want to remove those nodes from the things in the causal connection graph. True or not?
So by above, you mean before?
Before, that's right.
Right,
Is that
okay,
what we
yeah.
want to do, or do we want to show the complete flow? I think it would be useful to see. I mean, okay, so the disconnection, I see. At level 3, yeah, you're right. We want to remove the things before level T sub I, right?
If you just want to see the structure at specific time steps, then yes.
Okay, all right. Okay, so what we want then, how do we do this then? So what we want to do is from the T sub I, okay, so down here, we've got this, and we want to pick we've got this graph. We found those components that are specifically at level 3, right? So then what we want to do for causal connection graph is to get the subgraph. Okay, so let's do that for this case, okay? So here, the vertices specifically at level 3 would be, let's remove that, oops. Yeah, it's just this. Okay, so those are the vertices specifically at level 3, correct? Yes? No?
Yeah.
Okay.
Sounds like unless I'm missing some subtle
Okay,
thing.
all right. So then what we want to do
Or
is
possibly
pick
4.
out, we want the subgraph of line 64 with those vertices, right? Okay, so then according to this, those are 3 disconnected regions, right? Specifically at level 3, those are disconnected regions.
Which will always be the case. It's a space-like hypersurface.
Okay, then what should we be doing?
The time extenders case, the one I programmed.
So why don't you walk through then what you think we should be doing? Because you were saying that you didn't think that this was giving the correct results.
Wait, we need to take, okay, what was that function that was giving us list of future vertices?
Get causally connected regions.
Right, so we need to take a subset of those for the vertices we care about.
Yeah, right.
And then
exactly.
from that on, we do the same thing.
That's what I was trying to do here. Oh, you're saying we look at that the things for which we generate the causal. Can you guys help, please?
Yeah,
The things for which we are generating causal connection summary. You're saying that we don't want to consider in that original list of causally connected regions. We only want to consider those nodes that exist at this particular level. Is that right?
Yes.
Okay, fine. All right, so let's go all the way back here. Okay, so this is get causally connected regions. And so this, what we want here is causal connection graph at, effectively, which then has to also compute, which I'm surprised you can't compute, Jonathan, while you're computing this. Don't you have that?
Yeah, obviously I could. I mean, if you want me to modify the code, I can do that.
Why don't you make a version of it called get causally connected regions at?
Okay.
That just gives the ones at level T sub I.
Right.
I think this is useful as well, but that would also be useful. Okay. Sorry, let me just look at one thing here. Okay, let me know when you have that. Hold on 1 second.
Yeah, it's sent.
Okay, great. Sorry, I'm just dealing with a couple other things. Okay. Okay, fast work. All right, so this is now, so this is get causally connected region at. Okay, so I should just copy all of this. I'll probably want the Wolfram model case of that in a minute. All right, so now what we, I guess, want is to modify this code. Where was it? We want this code to be causal connection graph at, get causal connection regions at, and then causal connection summary. Okay, what does that mean? Is that what we expect? We can try running this. Should we try running this? Was that what we expected for that case?
Not necessarily. We need to highlight those vertices somehow.
Okay, well, we've already done that here, so let's do that this time around. Okay, so this would be causal connection summary at. Is that right? Is this what you think, Jonathan? Is this correct as far as you're concerned?
It's doing what you requested, I think.
Well, but do you think it's doing the right thing? I mean, so this is now saying, oh, looks like complete nonsense, right? This level, this is highlighting vertices 4, 9, and 10, but that's not what's appearing here.
Right, because the out component construction highlights the 4th level.
What level would you like to highlight?
You requested level 3, right?
Oh, so let's do that then. So okay, so this is.
If you change the causal connection summary at from 3 to 4, do you get the same result? That's what I'm wondering.
This one here.
No. Wait. What is that out component thing doing? When you and Max wrote that, I assumed you knew what you were doing, but what is that meant to be computing?
That's computing. The out component is the future light cone of 1, of vertex 1, right?
It should be 3, 7, not 4, 7, because we are computing level 3 here.
Sorry, what are you saying? Okay. This here should be those edges that are precisely that are contained on the leading edge of that light cone. That is, they are.
I don't think that's how causal graphs work.
Yeah, that's not the same as generations.
Yeah, my code is computing generations, i.e. time-separated layers.
Right, so
that's much better. So we should just take list of vertices from causal connection summary at, instead of recomputing from scratch here.
Yes, right.
Okay, so tell me what you
because look, I mean, you can immediately tell this is wrong because there are seven. There are meant to be 7 steps, and there are more than 7 layers.
Hold on. So what do we want to do here? So we want to take the first of this. So then we take this, and we compute. Let's say GS equals this, and then we would compute. Hold on, that would be GS there, and here we will take first slash at GS. Is that correct?
Right. But
I'm sorry?
well, the only problem, it will only give us one vertex from each component.
What will only give us one vertex? That's the summary, because we're doing the summary here.
Yes.
Also, that GS is not in scope.
I know.
And once we get the Wolfram models, we should use layered causal graph for layout.
Hold on. So that's the highlight graph of that. What's that 5 doing now? That's the time constraint. Okay, well, at least that agrees now. So that is the poor isolated object at that level. So this has no, okay, so here.
So that means there's only one component.
That's correct. So 8 to 11 is saying that relative to 8 claims to be able to reach 11, but 11 cannot reach 8. Am I making sense? So arguably here, we should actually draw this graph down to level 7, because otherwise we're not going to be able to tell.
Yeah.
See what I'm saying?
Right.
What connects to what. So let's draw that to level 7. Oh, for goodness sake.
Yeah, we should make it layered, otherwise you won't understand anything.
All right. Wait a minute, what did I just compute wrong? Did I do this wrong? GS. Oh, I just managed to make that into a layered digraph. Not completely useless, but fairly useless.
Yeah. Of the graphs Max said we'd had trouble understanding, that was probably not the one he had in mind.
Okay. Okay, so 11 is the representative of the connected components at that level. So that's claiming there are no, okay, so this 8 to 11 thing.
Yeah, 8 and 11 aren't actually causally connected, but something in the connected components of 8 is causally connected with the connected components of 11.
Oh, how could that happen?
No, that can happen. That's an intersection
yes,
of the future light cone.
Right. So I think when we do the vertex contraction, we should arguably rename the vertex to be the whole equivalence class.
That's just a nuisance to do.
Well, we should highlight all of them.
All right, okay.
Otherwise, you won't understand anything.
Right. I mean, this is pretty incomprehensible as it currently is, because we don't actually know what's causally connected to what. But that's a good sign. That's a very good sign.
What's a good sign?
That we're picking up the black holes.
Well, we're picking up this black hole.
Yeah, which we weren't doing yesterday. Well, my very naive code yesterday wasn't doing, but now we are.
Okay, but so in this case, do you believe there's a black hole here? Looks like it, actually. 11 looks like it's pretty black holed.
Yeah,
Right.
yeah, I believe that.
So that 8 is basically, so right now we don't have any cosmological event horizons here. Is that a true statement? All the things we're seeing here are black holes, not cosmological event horizons.
It looks like it.
All right, so let's go compute all of them, just for the hell of it. And then we can do the case, the Wolfram model case in a minute. And right now, let's just, this is one of these, you're not expected to understand this type of things. Let's just see what these come out like, and we can go back and relabel them later.
Well, one of the reasons I don't understand them, because we need to check if they're correct or not.
Fine. Okay, all right, so, wow, that's a weird one. Okay, so a lot of these have no, okay, so there's a black hole. Okay, what's this guy here? Oh, look at this one. Look at this.
Yeah,
look
that's
at this.
a cosmic
There's
event
cosmological
horizon.
event horizon.
Yep. Yeah, I think this is working. It's just as I say, without knowing the connected components, it's kind of hard to interpret what's going on. But the combinatorial structure is right.
Okay, so there's a cosmological event horizon. What's this thing here? Maybe we'll find a space tunnel in one of these.
That's a black hole. That can happen.
Is there a solution in which that happens?
But if you throw a black hole into another black hole, wouldn't it just happen?
Yeah, embarrassingly, I don't actually know the name for a solution for a nested black hole, but.
Does Jose? Is Jose still with us? Does he know?
You're discussing black holes inside black holes?
Yes.
Well, I would say that the event horizon is a unique structure. I mean, when you have a collision or something like that, it will form a single one out of two.
We understand. But look, we've just got a structure here that is a black hole inside a black hole. So let's say you numerically solve the Einstein equations with all of that random chaotic stuff that's happening inside the event horizon of a Schwarzschild black hole. Right?
Yeah, so you can have apparent horizons.
What's that?
I mean, there are these apparent horizons which are local structures, and those can be nested. But the event horizon, I think, is a unique thing. It's a unique thing that you measure from infinity.
I see what you're saying. You're saying you can't define an ordinary event horizon because within the black hole, within the first level event horizon, there's no infinity to look at with respect to which to measure another event horizon.
Right. If you try to find the inner one, it would cross at some point the outer one.
Okay, so what does this mean then here?
Well, these are nested. I mean, everything we're computing here is an apparent horizon. I mean, as they said, right? Because we can't compute the infinite causal graph.
Fair enough.
So these are nested apparent horizons, and yeah, as Jose said, if you ran this for long enough, they would become a single event horizon, but you'd have to run it for infinite time.
Okay, so there are a whole bunch of cosmological things here. It's pretty cool. Okay, so that one, okay, so wait a minute, 12 to 16, that's really weird.
Wait, why is there an edge from 12 to 16? That shouldn't happen if they're in the same generation.
Well, I don't understand this picture here.
Yeah, if you have an edge from something to something else, it means that something else will be on the next generation, by definition.
Well, I'm not sure what's actually happening here. Let's take a look at this guy. 12 to 16. What? This is a weird case. Look at this. So this 12 goes to 16 by a time-like edge, right? By a null edge, whatever, a causal edge.
No, it seems the graph on the right is correct, but they shouldn't be in the same generation. So computing generations is not.
Why can't they be in the same generation?
Because
by
they're
definition,
time-like separated.
Generation is defined as, the thing that causal edge goes to have one larger generation.
This corresponds to a non-globally hyperbolic spacetime. because there are time-like because there is no consistent way to foliate it into space-like hypersurfaces, right? Because within what we're seeing here is within a single generation, you can have time-like separated events.
Yeah, I understand.
So this is a failure of global hyperbolicity.
Okay, so
what do you mean? How do you define generations?
Because substitution system causal graph runs the substitution system for one generation, or it runs one iteration, then the next. And so all I'm doing is I'm computing up to the to get the third. I'm computing everything up to the third and everything up to the second, and then taking.
So these are multi-way causal graphs.
No, these are single.
But for single branch, multi-way causal graph for a single branch.
I presume that's what substitution system causal graph is doing, but
which is not the same as Wolfram model causal graphs.
Right.
Because the generations there are defined exactly as each next.
All right, let's take the same code and let's apply it, and we have to wrap fairly soon, but let's try to apply it to Wolfram models, okay? And because I think
and let's take generations from
that. Okay, so can we loop back and what was
but the taking generations is fine because your code already does that, Max, right? I mean, if I put in
I'm saying let's take generations from Wolfram model.
Yeah, no, but I'm saying that the code. I was assuming substitution system causal graph worked like Wolfram model, where the second argument was the generation count.
Which
but
I think
generation that's causal graph is not well, you get generation count for the whole graph, but you need to extract a layer from it. So the question is how.
No, but for a substitution system, there is no difference between iteration. The substitution system has a canonical updating order.
Somewhat.
So
it has a max scan canonical updating order.
So what? Okay, Stephen, what is the second argument in substitution system causal graph?
The number of max scan steps that have been made.
So it is a kind of generation.
I think so.
Okay, so yeah, so we're fine. This is, as I say, this is just a failure of global hyperbolicity, which won't happen.
So. Yeah, I think so. Which can happen.
Yeah,
I mean, it's a nice example actually, but it can happen. Okay, can we do the Wolfram model?
Well, that means it's a different kind of generation. Because the way Wolfram model computes them, you cannot have causal edges from one generation to the same one.
Yeah, like I say, the Wolfram model case enforces global hyperbolicity, which substitution system causal graph doesn't. But that's okay. We kind of knew that.
Okay, fair enough.
Okay, all right. So let's do the big case here. Okay, so we've already so basic bottom line here is we've successfully found that there are cases that have cosmological event horizons and black hole-like event horizons, which is kind of cool. We've not found any other we found this slightly more exotic structure with apparent horizons here, right? Someone's asking here, the cosmological event horizons differ because these are different connected parts of the universe. Each one is connected, but they simply can't reach one from another. Whereas the black hole case, you can get from one component of the universe to another component, but not back again. It's a one-way trip in the black hole. Whereas in this case, once you're in one of those components, you're stuck in that component. In both cases, you can get, in this case, one-way trip. This case, it's different components.
It's great. Actually, this is disconnected nice. Components.
What's that?
These are weakly disconnected components.
What? Well, what do you mean?
Well, they're saying there are no edges at all.
Well, I'm sorry, what? They're disconnected. I mean, there are no edges. What are you saying? I don't understand.
Well, anyway, I won't make any deep point. I'm just saying the difference between strongly and weakly connected components
is I see. It's the difference between the black hole case, which cares about the direction.
Yeah.
Okay, fine.
And by the way, this nested one on the right is not going to this. I mean, it's not going to collapse in the future because it seems like it already got to the repeating case.
Yes, I agree. So that
So
means
there's
there's a
anomalous we
component.
can have that, even though in real physics we might not be able to have it.
Well, I mean, so this is saying this is something where you can fall into black hole 11, and from there you can fall into the inner black hole 10. Right?
Yeah.
Okay, can we look now? Okay, let's loop back here and let's look at okay, so what do we need here? We need causal connection. What we're trying to get is causal connection summary at. We're trying to get this function, basically. Oops, where was it? We're trying to get this function for the Wolfram model case, right?
Yeah.
Okay, let's do it. All right, so what are we changing here? So first thing is your causal connection summary at. I have fed that into, I don't think your code, so your code uses, your code specifically calls into an evolution function, right, Jonathan?
Yes, so you need get Wolfram model causally connected regions at.
Okay.
Which is a bit of a handful, but that should be in the notebook I just sent.
All right, okay. That you just sent or that you said, oh, that you just sent, okay.
Yeah, I'm losing track. It's possible it was in the previous notebook. I honestly can't remember. Oh, it's blue, which indicates it probably wasn't.
Okay, all right, fine. So that goes in there. So then we have to map that through into, okay, here we go. That's this. Okay, that has no dependence on anything beyond that. Okay, so now we need the chain that gets the causally connected summary, whatever it is thing, right? So first thing we need is, okay, the summary at, I'm going to copy that into a different notebook here just so we keep track. The summary at, and that depends on causal connection graph at, which is there. Okay, let's go back down to the bottom. Okay, so now let's say, oh, I don't know whether we want to do this. Let's just call it WM. It's a hack. But it's getting late, so we're going to have to hack it. Now, some of these things here, oh no, that's going to make a causal graph, so it's not a problem. So this is now WM summary at, WM causal graph at. Okay, does this look right? Now we need to go back up here. And this
It should just be resource system Wolfram model and then causal graph at the end.
well, what's the initial condition?
Automatic.
And that is just, no, is that going to work?
Yeah.
Okay. So then here,
Well, it needs to be WM. Sorry, it should be WM causal connection summary at, but apart from that, it should be fine.
okay. All right, so now what I did previously, I actually had a nice collection of these things. So let me just look there. Black holes 2. I believe I had a line where I just had, maybe it's in black holes 1. Well, do we happen to know where the initial conditions, I was looking for a 2-2 goes to 3-2. See, I think we maybe had it here. Here we go. Okay, so let's do a random sample. All rules 32, 6, for example, okay? Let's do %87 here. All right, let's see. It'll be amazing if this works. Well, it did something. Boy, these are so similar looking to the ones for string systems. Okay, let's look at this. Do we believe this? 5.
Well, it's really hard. Well, there are only 3 of them. So presumably 6 and whatever is to the left of 6 are in the same component.
Yes. All right. Well,
Yeah, and by the way, you shouldn't be using layered digraph embedding. You should be using layered causal graph, because that would give us correct layers.
Okay, hold on. Where should I be using layered causal graph?
Instead of causal graph property. Okay, that's better.
Okay, so these are now
yeah, so now we know there's only 3 of them.
only 3 watts. Oh, things.
In the last example, and the one on the left has to be in the same component as 6 because they're intersecting.
Yeah, which we can see. Right, so there, it's intersecting like that, right? All right, let's run the real case here.
I don't understand why 6 and 5 are not. Oh, okay, because not everything can be reached from 5, but everything can be reached from 6.
Okay, here goes. You know what? I'm going to stop making this 200% because otherwise it's going to be absolutely huge. We are at 2,000 out of 4,700. So let's see. It makes a big difference to have a factor of 100 difference in speed of computer. All right. We're almost there. Let's see what kind of exotic. Oh, you know what I didn't do? I didn't put the interactive selector around this. We're not going to know what's what. I may have to rerun this. Okay, it's still grinding. I see it's generating generating all those causal graphs.
It means we have the fun of counting, top to bottom.
That's absolutely absurd. It's a stupid idea. This is going to take forever because it's sending all the data back from all the 100 computers.
So I'm afraid people on the live stream won't be able to see anything. Even on my screen, it's kind of small.
Okay, this has everything, but it is not displaying everything here. All right, so that's the complete set of results, all 4,700 of them. What we should probably do is, given the right-hand sides here, given these second things here, we should basically, you know what we should do? We should ignore the first. We should just compute. All right, let's do this. Let's compute. Okay, I'm gonna go back to 200% here. Okay, I've got a better idea here. Let us do the following. Let us compute. I just want to find out what are the structures, what are the causal structures that we can get. So here, what I'm going to suggest is let's remove this causal graph thing. Boy, I'm just trying to understand how. I want to get a representative sample. Well, here, there's an easy way to do this to begin with. Highlight graph. So we don't need that first thing there. We just need that graph. And now let's say index graph, because we just don't need, we don't care about that. We don't care about that structure. We just want this. We would set that index graph. And now the first thing I want to do is just find out. So I just want to find out how many of each thing there are. Okay? Make sense? So this is now not bothering to compute. This is only computing the causal connection summaries. So I just want to see what kind of exotic things occur. And I believe index graph will allow us to, will cause them to, it doesn't matter what the labels are. That is profoundly boring, right? So that's saying, oh, I see. Oh, that's kind of an amusing one. Okay, so these are the cases. Right?
Oh, that's, yeah, black hole in an expanding universe.
Yes.
Cool.
Okay, so what we have here.
Should you maybe go to higher level than 4?
Well, okay, hold on. Let's just, first of all, there's a really very basic thing here, which I'm embarrassed to do and recompute everything, but I'm going to do it anyway because we're going to do the next case later. Just so we can see what the heck is going on. Okay, so these are the different cases, and this is out of 4,700 rules. And then we should figure out what's what in a minute. We can get, for each of these, we probably should just get the rules and gather them for each thing. Very boring to watch this. This is where we haven't done very many of these on live streams yet, is hunts. I mean, this is an early hunt. And this is, I mean, often these things have to be left to run for days. But this one should go, I don't know why this one is going slower than before. Okay, there we go. That was all I wanted to do. Okay, so that case there, what is that one? That's probably when the whole thing died out. This case here is the case of two disjoint cosmological regions, of which that's fairly common. It's very common to have a universe without black holes in it. Okay, all right. So now you say we should try a different case here. Are you saying, what are you suggesting we try here?
More steps instead of 4 in case black holes didn't have time to form yet.
Okay, and actually we can get rid of this G equals, we don't need this, right? We just need the GS case, correct?
Yes.
There's no reason to compute the causal graph there.
Right.
Okay, so what are you saying? You're saying we try 5 here. Do we want to be as dangerous as to try 8 here?
Well, at least maybe even 9.
Let's live really dangerously. Let's put 10 in here. And worst case is it'll time out, right? The time constraint will work through the Wolfram model code, right?
Yeah, should.
That sounds like famous last words if I ever heard them.
Well, we could also take a sample of the 47, although it is interesting that we only have a single case where there's this black hole plus cosmological, plus separate part of the universe.
That seems to be going faster, actually.
That looks more diverse. Ooh. That last thing's kind of cool.
Okay, what the heck is it?
That's 3 nested apparent horizons.
Well, I understand, but okay. So this is 2 black holes, 2 disjoint regions of the universe with both with black holes in them.
Mhm.
What are these things here? That's 2 black holes.
Two black
right?
holes. Yeah,
Two black holes
just
in
2
the
black holes.
Right.
Ordinary ones.
I don't know why these 3 are different. They probably, oh, I see, they have different labeling because of where in the causal graph, even in the index graph, they work differently. Okay,
Right.
so this is the universe breaks up into separate cosmological pieces. This is and these are various exotic nested black hole solutions.
This is pretty fun. Yeah.
It is, yes.
Yeah, we need to find what the rule is. I mean,
Yes. Okay, let's do that. Hold on.
and also, can we do canonical graph instead of index graph because they're small, so it shouldn't
Yes.
flow.
Okay, all right, fine. Okay, hold on. Let me just let's write this correctly so that we actually get what the rules are, and then we can go through and pick it out. Okay, canonical graph. You're saying do canonical graph here. And then what we want to do is, instead of saying counts, I want to say gather. So what I want to do here is I want to say framed of this, but I want to say hash, comma that. And then I want to say, and then I want to say gather by. Am I correct? Gather by last. And then I want to say there, let's take the first up to the first 3, okay? Make sense to everybody?
Yeah.
Take
Yep.
hash up to 3. And then comma. Actually, what I want to do is something slightly different. I want to say hash arrow take, no, last of hash arrow take that, map that, and then I want to say resource function well, we could also just compute the causal graphs. Well, no, let's do this. Resource function of interactive list selector. Did I get this right? Okay, and let me just, for the hell of it here, just to check that we're getting this right, let's say random sample of this, comma 40 or something, just to do a quick one. That was not a good sign. That just beeped at us.
Yeah,
That is very disappointing. What happened?
So this is the same rules as last time. So if it's a crash and set replace, it will be random one.
Something went wrong here. Okay, so
Well, it crashed.
Could it have been a parallel map monitored bug?
well, not a bug, but just these machines are so, I mean, it's crazy.
No, the kernel
Crazy. I mean,
crashed.
a random little,
So it is a bug.
what's that?
The kernel crashed, so it is a bug. The question is whether it's a bug in set replace or in the kernel.
Okay, let's try it again.
This isn't going to work. Intersection rule isn't defined.
Which rule?
Intersection rule. The function intersection rule is not defined.
Okay. Oh no.
And your parallel kernels have noticed.
Yeah. Okay, where is intersection rule? Let's go back up here.
There you go.
That is a lot of splatting. Look at that thing. And it's still running and it's not going to finish. So let me kill the kernel here. Oh boy. You know, I'm telling you, this when you're running all of these different kernels and things, it's just a frigging wild west of stuff going on.
We should start using the remote submits that Jesse is making.
Well, and have it run on AWS instead of running on the servers in my house. I mean, what difference?
Well, we will be able to run them on your computers at some point.
Yeah, no, I agree. Okay, so let's try and figure out what happened here.
I think we're okay. We should just be able to rerun this.
All right. Ah, sigh. You know, I think what's happening here, it's making SSH connections and it's going through and the other question is I might want to actually kill off zombie processors on these machines because that's another thing that can happen. Oh, come on. What is going on here? What is going on? This is no different from what we did before, right? Did we do something different here?
No, other than the interactive list selector and the random sample.
I don't understand what this is saying here. This is 0.2 of the way through something which is 48 out of 40. What on earth is going on?
Yeah, that means some of them have crashed. So some parallel kernels have crashed. So it's overcounting because it has to repeat the same computation multiple times.
Is it possible that the other things are just running on those computers and have gone out of control and are burning up the memory of those computers?
It is possible.
All right, let me see if I can run the thing that the emergency kernel extermination system.
The zombie detonator.
Yeah, right. This is one of those. Okay, hold on. Let me go find it. Local functions. Okay, let's see what this does. Kill rogue kernels. Well, let's see what this is going to do. Kill rogue kernels function. Let's hope it's got the right hosts. All right, let's try it. Well, here, let's put it in here just for fun. Well, there definitely were rogue kernels. Look at that. Look at all those rogues.
That's a lot of zombies.
Yeah, on those machines. Okay. All right.
I'm wondering, shouldn't these kernels self-terminate if they cannot
Of course,
contact the
they're
original
supposed to. Yes, they when their parent link dies, they should terminate. But unfortunately, operating systems don't do that correctly. It is not our fault. It's an operating system issue because the thing has lost its parent link, right? So it should terminate.
This is the bane of the theorem prover, or was for a long time.
You're saying
so-
because the kernel is computing something else, but
It-
it can still periodically check for the parent link. Why?
It's supposed to. I don't know why it doesn't work. Okay. Maybe you can investigate that, Max. Okay, so let's look at this. Let's try running this again. See whether, oh gosh, it's going to start up all the kernels again.
After how much debugging do we lose the efficiency gain of having 100 parallel kernels?
No, that's a good question. It's quite a bit, actually.
Uh-oh.
I don't understand this. This thing is really dying. Okay, it's very dead. All right, I do not understand what's going on here. I mean, it was working just fine before. I think we may have to end this on a cliffhanger because I don't see how to. Oh shoot! We should be able to debug this. Okay, what is going on? First of all, let's run the rogue kernel killer again. So there's still rogue kernels running. No, there were no rogue kernels left running. Okay, a graph object is expected at position 1 in vertex out component of blah. So is there some definition that we haven't made again here?
It might be. Yeah, let's rerun everything and just check.
Can we just run a few cases without
Yes,
parallel
obviously.
kernels?
Right, without stupid parallel kernels. I agree.
Very good call.
Okay. All right, let's try random sample here of like 4 rules. Okay, now let's try this. Okay, that seems to work fine.
That's the only
non-trivial. Is there any
non-trivial.
possibility that canonical graph is failing on one of these? Like the null graph? No, that seemed to work fine. All right, so let's try here. Let's just look at this. Okay, so let's try replacing parallel map monitored with map here for a moment. And let's just try doing this for 5 cases.
We're all good.
Yep, that looks fine. All right, let's now try starting parallel evaluate of $machine name. Yeah, Richard on our live stream is asking very reasonable questions about why SSH connections aren't persistently kept. I may be wrong about what's going on there. Okay, so we've now created those things. So now let's try. Okay, well, I guess we just try the big thing again because there doesn't seem to be any reason why this shouldn't work. Famous last words. Okay, interactive list selector of. Oh yeah, we know the interactive list selector works because it just worked there.
Yeah.
Okay, come on, don't. What the heck is going on here?
That really seems like they're crashing.
State defunct doesn't sound too good.
Wait, did they all crash, including the master kernel?
Yes, everything crashed, including the master kernel.
But it works sequentially. Or maybe it doesn't work for 40 cases. Oh, you're doing random sample. So every time it's a different subset. So it's possible that some of them do crash the kernel and some don't.
No, it's not, because we just ran it before for everything.
It's random sample without a seed.
No. We ran it for the whole collection up here. This is everything. We ran the whole thing here.
Was it the same? Wait, if it's the same code, why are we rerunning it?
Because we want to
were
get
rerunning it
separate
to be
lists.
gather instead of counts.
Huh.
Is there any possibility that there's some definition we don't have here?
If there were a definition we didn't have, it would show up on the sequential code.
All right.
Is it possible there's a definition that's not getting propagated down to a parallel kernel?
No, but then
Well, unless it's a function repository function that's not loaded, or
Brian on our live stream says, I could be dead wrong. Maybe
Yes.
parallel map monitored needs some work. Yeah, I mean,
I think that's an understatement.
function repository, not somewhere else.
yeah, when I wrote it originally, I never expected that anybody else would ever use it. So yeah, it does need some work.
Well, let's do this. Do you think we can just not use parallel map monitored? We could just use parallel map. Maybe there's something going wrong. What's so weird here? Let's do this. Let's try to evaluate. I can't imagine why this would make a difference here. Forget the gather by. Just do this. TLDR of this stream, parallel programming is still hard. Well, you know, yes, it's hard because these stupid machines just, okay, let's try this again.
But the great irony is that one of the reasons, parallel computing could be a lot easier if we make further progress on the physics project.
That's true.
We have a chicken and egg problem.
What's happening here? Why is this just hanging? Why is it not even? Wasn't even starting these kernels. I could also reset this so it's not trying to do it in as many kernels. But I mean, or maybe there's something wrong with a machine called Threadripper. I don't know.
I was going to say, all the glitches seem to be the Threadripper thing.
Oh, for goodness sake!
Yeah, actually, can we just see if that error occurs for any of the things other than Threadripper?
We already died. The master kernel already died. Okay, let's take Threadripper out of the parallelization.
Yeah, I think that's a good plan.
Yeah. Is it possible it has a different version of the kernel or something like this?
It's possible. Yeah, I mean, the distribution of the kernels is not. Yeah, that's possible. Somebody's asking, maybe it's an AMD problem. It might be. It might be that. I mean, this is the Wild West, unfortunately, still. Okay, so let's do a parallel evaluate. Dollar version, well, dollar machine name, dollar version. Let's just see with Threadripper in the picture. Let's see what happens. Let's just see whether they're all the same version. Bit frustrating, we can get as far as black holes, but we can't get as far as no, they're all the same. Well, I mean, that's a Linux machine, but so what?
Wait, they're not the same.
They're all the
Today
same.
is different.
What's that?
Well, they're the same as the other one. Not the same
those
as
are
the
slightly
backup.
That's a little weird that those are different. 12.1.0, but they're all 12.1.0s. So there's nothing trying to run 12.2 or anything weird like that. All right, let us try taking in parallel kernel configuration. And if anybody is paying attention here from our team watching the live stream, could you make a note for Roger that I'm doing this so he can back this out? Remote kernels. We are going to disable Threadripper. Oh, it's 32 cores. So sad. Well, it's going to make this a lot slower, but let's try it again. The other thing that occurs to me is that there might be a problem in the definition distribution to do with the way that this is the sequence of those rules.
Yeah, that seems plausible.
That's a good thing about using Docker, because then everything is guaranteed to be the same.
Okay, let's try this now.
Uh-oh, it begins.
But why is it going to Threadripper? We just
Did you close kernels after removing it?
What is an EYPC? I should get the 64 core version of this. Yeah, I mean, this is a quite new machine as well. What the heck is going on here?
Yeah, Max makes a good point, right? You already launched these kernels. So
well,
you have to.
I didn't now. So now we will not get Threadripper. All right, let's try one more time. Okay, local, fine. Why are there only 25? Oh, I know why. Because I don't launch 28. I've got 28 cores on my desktop machine, but I don't launch all of them because otherwise the machine grinds to a halt. Oh, come on.
Wait, local is failing.
Okay, so it's not Threadripper specific.
Not only that, it's also not to do with the distribution of definitions, because local will not require definitions to be redistributed.
Right, something very weird
Why?
is going on.
It would.
No, it doesn't. It doesn't. It doesn't do that.
It's still a different process.
Oh, that's true. Yeah, you're
Although
right.
it means it wouldn't have anything to do with Parklet installation, anything like that.
Right. It won't be Packlets, and it won't be yeah, this is okay. I'm going to try one more thing. Okay. I'm going to try just restarting the whole shebang here. And then if this doesn't work, I'm afraid it's time for my dinner. Okay. All right, here we go. So sad, we were getting so close. All right, try it one more time. All right, I'm going to just pull this out just for the sake of, so it's repeatable. And I'm going to do something else as well. I'm going to, well, first of all, okay, so with map, we believe this works. Should we try this with map just one time? Let's try it with map just to see that it works locally. That's going to be really slow, but anyway, let's try it. See, this is the problem with okay.
It ran.
No, now it crashed at the
Oh, is that? Oh, I didn't notice.
So essentially, the code with Kazaa crashes and the one without doesn't.
The code what?
So we just used Kazaa and everything else is the same. And
No. We didn't even use gathered by here. This crashed.
There was a different compared to the previous one.
Okay, but so now let's do this. All right, let's do this here. And then let us go through here in the map and let us go ahead and echo I mean, it's really weird that it crashed after this. Okay, so I'm going to echo, actually, I'm going to echo each thing as it comes out. It just crashed. It just crashed. So the second one of these caused it to crash.
So what exactly is the difference between this one and the one that worked before?
Well, as you pointed out, there are random rules involved. So it could have been, so let's rerun this. But what's really weird is what could cause it to crash. I'm suspicious about Max's code here, but let's not go there yet. Okay, so let's do this. Now let's echo this before we do that. So we'll see if this crashes, we'll see what the actual, it'll echo that before it echoes. In fact, why don't we go ahead and echo them in sequence there. Oh, no, let's echo that. Let's do this. Okay, that crashed. 1, 2, 2, 3. So this one we know crashes.
You can just run Wolfram model with it.
Yeah, I will. Okay, automatic, let's say 10 steps. I have a bad feeling about this, that what's going on. Well, I have a bad feeling, but anyway, lead causal graph. I mean, this might be huge. We may need a time constraint here.
Or it could be trivial.
Yeah, it's trivial. Okay. So now let's run this. Okay, let's evaluate this. And we're computing this quantity, WM causal graph summary at, with that thing. And then, such a shame, we've gotten so far here. Growl. Okay. All right, so now WM causal summary at, let's do this. I predict this is not going to crash. And it didn't. Just produced an empty thing.
It'd be pretty embarrassing if it failed on a 2-event case.
Yeah. Okay.
So what's going wrong?
What about canonical graph of that?
I tried that before, but let's try it.
Can you try a table of hundreds of those? Yeah, and can you do table of hundreds of canonical graph of empty graph? Yeah, that's better.
It crashed.
Good spot.
Okay, can you just do Wolfram model of, just do Wolfram model 100 times, the function above? Because it might be a random bug in set replace.
Oh, you want me to try it again?
Yeah, try it again. Try for 500 without showing the result.
This is the problem. I mean, you know, just for people's information, the way this works is it has low-level C++ code that it's calling ultimately to do various things, and that's
That returned.
directly into the system. What's that?
Did that return? Looks like it returned.
Yeah, it returned.
Okay, now try the line below without canonical graph 50 times.
This is very fun.
Oh, it's very horrifying.
Brian on the live stream points out that this is the cosmic censorship conjecture in action, trying to prevent us from learning about black holes.
What's inside black holes? Yeah.
Yeah.
Right. Well, that could be ultimately
So it has a long arm.
Okay, so then this. Worked just fine.
And now map.
Another 50 or 100.
Well, now let's do the canonical graph.
Yeah, can we map canonical graph over that?
Yeah, just canonical graph of an empty graph a bunch of times.
No problem.
That's okay.
I'll try it again. Maybe 50 is not enough.
I crashed.
This is so weird.
It's probably 50, just not enough. Try both of them for 500.
You know, this is what experimental scientists have to deal with all the time. Is things sort of randomly failing like this. And us computational folk usually have it really easy.
Well, we had a bad thing in set replace recently where it would crash, but not on master branch, on some other branch. But with CI will still report then it passes because the return code was 0.
What? Because in the continuous integration?
So it crashed, but the return code was 0. Yeah. So CI returned it as passed, all tests passed. And it's good seeing somebody spotted that, because otherwise.
Okay, so that succeeded there. But now the canonical graph case, which I mean, has
can you just do? Both of them succeeded.
No. I didn't do the canonical graph case.
Yeah, can just do canonical graph of the output only, separately.
Of this one.
Yeah.
Fine. Just worked.
Interesting.
So shall I do this canonical graph thing here?
Well, we know this crashes.
What do you mean we know this crashes? We don't know
It crashed before.
Yeah, it did.
Well, you can try it again.
You can echo I, see where it crashes.
Yeah, I'm going to monitor this for I. Is that right? Did I get this right? I think I did.
Yeah, that's okay.
See, I think it's crashing at the very end, which is even more bizarre. Like it's crashing when it gives up memory or something.
Yeah, I mean, someone on the live stream is saying that they reckon it's a memory leak.
Yeah, but that's the generic. I mean, yes, I agree that that's what one would normally. But I mean,
but can you check your memory? I mean, if you use too much, well, actually on the Mac, it shouldn't be a problem because it will just keep using swap until your hard drive.
Yeah, right. And I've got very big configuration here. I can, if I can figure it out.
It
worked this time.
Oh no, and then it crashed.
I told you it crashed at the end.
That's very weird.
At the very end.
So is that some kind of data return issue?
Possibly.
Is it trying to return something to the front end and the front end is freaking out?
No, that's
But
very.
it's not front end, it's a kernel that crashed. Unless it's some kind of weird call to the kernel from the front end at the end.
This
And
is
also
really...
we don't return anything because there's a semicolon at the end.
Yeah, right. But I'm wondering if something's still getting passed even though there's no return.
No, the pathway, the code path here is so deep inside its, low level of its brainstem. There's no way this can, okay, this is something weird going on, needless to say. And I think set replace is implicated, but set replace is a library link function. Is that correct?
Yes. I don't see how it would implicate it unless it overrides some kernel memory. Well, that could happen. Maybe
Yes,
it overrides kernel memory and nobody notices until until the final step. Given that it's so simple, you could try to
when we added the 10 there.
Yeah, that's good.
Had 10. We already had 10 here.
That's a good question.
Can you try doing method goes to symbolic in the Wolfram model? Because these graphs are so small, they would be fast enough anyway.
Okay, but the thing that is totally mysterious is this worked just fine up here.
Well, if it's a memory override, that's
no, but it doesn't make sense because it worked just fine here.
Well, yes, it overrides some memory, and then it's a question of memory arrangement of whether it's
no, it's repeatedly crashing right now.
Well, yes, because it's in a different way of kernel setup. The memory goes to different places.
I understand the claim, but I think that's, that is a hypothesis made to fit the data, so to speak. And I mean, or whatever. I mean, it's a. Okay, let's just think about what is happening here. So, first of all, why would it fail right when it is returning?
Just try Wolfram model method goes to symbolic.
Yeah, I will, but I won't start running that exact same code, just in case there's something that we're missing here. Okay, I think this is going to crash, but I don't know. And so this is the exact same thing, except I think I've re-enabled Threadripper. We're doing the exact okay, this is much more mysterious. See this? This is working. What did we do wrong here? Something weird is wrong.
Well, yes, we need to try the symbolic case of Wolfram model.
No, but look at this. This is the exact thing we were just trying to do before, and it's working.
Well, almost, but because it does slightly different things, the memory, arranged in a slightly different way.
Well, the only thing I can see that's different is the index graph here.
Yeah. Well, these memory things are very hard to debug.
Of course, but I mean, this is what's implicated here is Wolfram model scribbling on kernel memory.
Yes.
Which is very bad and needs to be, hunted down.
And also we should try to do it without resource function because it changed slightly since then.
Okay. Ooh, that's interesting. Look at that. That's different. That's not what we got before. That's kind of weird. So there are 42 cases there where, okay, but otherwise that looked the same. So just for the hell of it, let's try and do this without the counts so that we could then do the gathering, because this should just work. And let's not worry about the index graph as canonical graph, because I would have my dinner. And then this should be that, gather by last. And this is all okay. Okay, do you think it's correct? The gather by wait a minute, what did we do here? This is oh drat. You see what I did wrong here? I didn't keep the rule here. I have to redo this. See that? This should be hash like that because I didn't keep what the rule was. Okay, I cannot imagine. Why is this different? Why is this behaving okay and the other one was not? I mean,
Well, it's index graph, not canonical graph.
I know that. But why canonical graph? I mean, so canonical graph must be interacting with some memory scribbling on the part of.
Yeah, that would be my guess.
That is really wild.
Well, these things are typically wild.
Okay. I don't know why this is slow.
It's just a lot of stuff.
Oh, well, what did we do? We gathered the wrong thing here. Somehow this went wrong. Oh, maybe those are distinct index graphs?
Yeah, I mean, that could happen, right? That's why we used canonical graph.
No, but I think there's something else going on here. This is, okay, hold on. I think we just have a trivial bug in this code here. What we've got here, before we do the gather by, is let's just take %12, -5, for example. Okay, so here are those, and we've got rules, and we're saying gather by. Well, we could say, am I right that we should be doing gather by of last here? Because that's what counts will do the same thing that gather by would do.
Wait, is it last or is it last of last?
No, each one of those is just a single thing there. Oh, I did something much stupider than that. That is embarrassing. That is embarrassing. Look what I did. Look what I did. I put the framed around the whole thing.
Yeah, but that's what I'm asking. So the part specification should be able to. The framed is just the head, presumably, right?
I know that, but let's get rid of that because that was goofy. Because that should have been just for the graph there.
Right, but that shouldn't mess up the last.
Yes, it should. It was picking the last, as you say. It should have been the last of the last.
Yeah. Okay. Right. That makes sense.
Okay, come on, don't crash. Very good. Okay, here we go. Thought I'd asked it to take up to 3. Oh, I see. These ones only have 1. Okay, so these are samples of different cases with different. Okay, so should we look at?
I want to see the 3 nested apparent horizons case.
This one here.
That's a cool one. Yeah.
Okay, so this one Oh, actually, you know what I was doing here? Oh, I see. This is first of that. Oh, I did this stupid thing there. Never mind. It doesn't
If we're
matter.
outputting the rule, do we need to have the interactive selector?
No, because I shouldn't have been outputting the rule.
Right.
Okay. Because what I was actually doing here, this is completely goofy, but that's okay. That's okay. All right, so we have this rule, and let's go ahead and look at its causal graph. So this should be this rule, automatic. What were we doing? 10 steps and layered causal graph, right? What the heck is that doing?
That makes sense.
And what
Yeah.
way does that make sense? You're saying there are 3 black. Where are the
Right.
black holes here?
So the part to the right is normal space because it's all connected.
Right.
But the left ones are unreachable.
Oh, I see. I see. So this is actually a cool.
This is very
a
Penrosian, yeah.
really cool rule because it has a very simple Minkowski-like structure here.
What does the state look like?
Yeah, what does a state look like? Good question.
It's presumably going to be manifoldy, right?
Well, let's see. States.
Plots list. Ah. Amazing.
What the heck is this? What is this? Okay, so let's understand what's happening here. So this is Minkowski space, basically. That circular region is something with a simple back and forth causal connectivity.
Right. And then each one of those threads is a black hole-y thing.
But why aren't we seeing more black holes here then?
Well, because we only went up to 5 steps, remember?
What do you mean?
No, but this causal graph has more than that.
Yes, but our detector only went up to 5. The initial only went up to 5. So we only have the states in the 5th thing there.
Well, this causal graph only has 3 also.
Let's just see what happens if we go to like 25 steps in the causal graph. So it's gonna look very, it's gonna look very much like that.
Right. So presumably, if we change the 5 to a 10 or something, we'd see a lot more.
So it has a generator on the left, which produces something.
Yes, but that causal graph. So in this thing here, what we're basically seeing is, this is a nice example, actually. I mean, there's sort of the ordinary universe, and then it's extruding black holes here. But why is it doing that hierarchically?
No, there's only one. There are a finite number of black holes. So those branches are not black holes.
Why not?
Well, because we only got 3 of those.
No, but that's because we only went to 5 steps.
Okay, can you try more steps?
What's that?
Can you try more steps?
Yeah.
I predict it's not going to increase so very much.
Okay, so you say let's try 7 steps and 10.
7 and 14 probably, so that goes far enough.
Wait a second, why did this give that?
You need more than 10.
No, but I don't understand why this rule. Okay, well, let's try 14 there. Oh yeah, okay.
There you go.
Well, let's try this going out to like 20 and check that doesn't change.
Right, so it's not more black holes, it's the same number of black holes. Because black holes are things on the left.
Yeah. You're right. You're right.
Okay, then I don't understand where they are in space-time. So explain that. So hold on.
You mean in space?
So there seems to be a branch that produces something. which is
Okay,
different.
so let's go ahead and do this. Okay, so what appears to be happening is that these seem to not change as we increase above 20 steps. And this seems to not change as we increase t above about 5 steps, right?
Right.
So let's go back up here, try to understand in space-time what's going on.
You mean in space?
Space, yes. What other...
What's that? What's that thing? What's that thing coming off that big thread?
What you're looking up here?
No, I mean any of the late time ones. There's a single filament that's longer than all the others, and it has a protuberance.
Right.
Unlike all of the others.
Let's go investigate the protuberance. Okay, so let's go get that thing. Let me just get the graph, because this is just.
Isn't it a double edge?
Well, let's find out. Okay, so let's say final state here, and then let's say graph. Can you do this directly, Max, in the code now?
Return graph? No,
Yeah.
you can't.
Okay, so there it is. So let's look at the 3D version of that. By the way, we should have this.
Yes, I reckon that protuberance is what's yielding these 3 black holes that Max is saying exist on the left of the causal diagram.
Yeah.
Okay, so hold on. Oops. So wait a second. This is where we need the VR system. Okay, so
that thing there.
Look at what's happening at the end of that. Look at that. Look at that. All these other ones have an outgoing arrow.
Yeah, but there's one where it's bidirectional.
Yeah, so that's a source of some kind.
But look at these here. Okay, so these here, look.
Okay, my guess would be that the other branches don't evolve. They just get produced in the circle and go outwards. But this one probably does something there.
Yeah, but why?
Go in the circles.
Look, what's happening is in this circle, there are these outgoing. There are these things that are outgoing. Each one of these is an outgoing piece, right? That one has an outgoing piece. All the other tentacles are pure. I don't mean outgoing. There has a divergence basically. From that point,
all the others just go in the direction of the filament.
Yes, but this is also a generator in some way. So let's look at that. If we look up here.
Can we check where the events are?
How do we do that?
Event states plot list.
What should I do?
So it's event states plots list. And then, it will be a bit inefficient, but we have to do it for...
Okay, how do I do that? To 10 events?
So it would do each event, not every generation. So 10 might be too much.
3.
Well, let's start with 3, okay. So you need more than 3. I think that's too much. Oh, okay. So now we can see where is it updating.
So wait a minute. I mean, it's extruding these hairs.
And it from time to time it does do something at the protuberance over there. You can see.
Yeah.
Wait a minute. So what's happening here? So this. I mean, the main circle. But by the way, we could try a different initial condition and see what happens. So many of the events are on the main circle, but some are in that particular filament. Is that true?
Looks like it.
Yeah.
But yeah, this does look like something that's going to be fairly initial condition dependent.
Well, it's also the case that in a sense, these hairs I don't quite understand these hairs, but I think they're growing the same way that hairs, for those of us who still have hair that grows on their heads, so to speak,
Yeah, exactly.
grows in the sense it's the base that grows, right?
Yeah, so it
It's not
seems
growing
what's
inside.
happening is that, yeah, so this saying, one of them is long and it has a structure which is also growing.
Mm-hmm.
So
Whereas the other
presumably
basically-
that's why it has, yeah, because something, let's see. Yeah, I guess you need to start there and then you go to the main circle and you get into this grid in the causal graph. But you can't
Where's
go
the
back,
grid? The grid is from the main circle. Is that what you think?
I guess, because it's growing.
Let's do the following. Let's make the main circle. Let's make the initial condition instead of automatic here. Let's make the initial condition. Let's just try the first sort of trivial thing, which is to make the initial condition 2. So right now we'll have, let's make it a square. Okay, 1, 2, 2, 3, 3, 4, 4, 1. Am I right? This may be very dangerous. Let's see. Let's ratchet that down a bit. Oh, great. No growth.
1, 2, 3 would match to that.
Right.
The ones go in opposite directions.
Okay, all right, fine. So forget that.
Just reverse, no, reverse 2 of them. So do 1, 2, 3, 2, and then 3, 4, 1, 4.
It's a harmonic oscillator.
Or a shield ladder or something. More like a shield ladder, right? Because it's in the
Right.
causal graph.
Mhm.
Okay, but let's try looking here at if we do just a 0, 0, let's do like 8 of those or something. Oh my gosh. I suspected this. This is in the, so I predict that in the spatial graph, this is going to end up being a higher dimensional spatial graph. And then there's a question of what does the black hole structure of this thing look like, which we can find out in just a moment here. Let's be a little bit more conservative there. I see. Oh no, okay, so it's basically just a multi-looped creature.
Yeah, it's still one-dimensional, but just more hairy.
Well, it's got more sort of compartments in there.
Hmm.
Okay, so let's try this thing with, where was it? Where was our actual black hole detector? Here we go. So what do you reckon? I reckon it's going to have many more black holes in that structure.
Yeah, because you can see there are a bunch of filaments that have many protuberances on them.
So it's going to have much more nesting in the structure.
Yep.
Oops.
Or not.
Oops.
Interesting.
We are wrong. All right, let's try as a function.
Can we run that for a later initial time?
Later initial time.
Yeah, like 12 or something.
Sorry.
Interesting.
Okay, so let's try initial time 7 here, and let's try as a function of 8, so to speak.
Oh, but does it have this protuberance in there?
I thought that's what those, you see that big filament on the right? I thought that's what those subfilaments were, but maybe they're not.
No, well, I think we have to look at what that graph looks like.
Huh.
Oh boy, that's not what I expected at all. So this means the universe is staying completely connected here, but in these cases, it's forming these weird nested black holes. The automatic initial condition just does 2, 0. It's the minimal initial condition that makes this grow, which is the left-hand side with all the element names numbers to 0. All right, just because I'm curious, I just want to do this up to, let's say, 15 or something, and I want to, let's just make that 25. And we should be using parallelism here because this is very inefficient. Oh, come on. Oh, there we go. Was this there before?
No. It was because we ran to a later time. I'm not convinced by many of these single dot ones.
You think that they're really going to break up?
I don't know. Maybe I'm wrong.
Well, let's look at the one for the 3 case, which I think is the simplest case here. So let's look at that case in particular. So let's look at the causal graph for that case. Okay, that's already kind of messy thing.
But it doesn't have those obvious 3 things that Max pointed out on the last one. It looks very connected.
It does look very, very connected. So let's go.
Maybe it's right. Maybe it's right.
So this is saying, at least with this updating order, and I mean, we could also look at the multi-way graph for this stuff, but although that's more exotic. I mean, that also is interesting because, if the multi-way graph is different, that's saying that there will be a black hole on some branches of the multi-way causal graph and not on other ones, which is itself quite interesting. What is the interpretation of that? In other words, if there's a black hole that forms, if you look at one slice of the multi-way causal graph, but not on another slice of the multi-way causal graph, what does it mean? It means one place in quantum space.
What's weird about it?
I'm afraid my dinner is going to be cold if I leave it much longer here. Just terrible. That's terrible. This can affect the fate of black holes in the universe.
You should get some Soylent, Steven, then you don't have to stop doing physics to have dinner.
All right, hold on. I really want to go on with this a little bit. So let's okay, so we're trying to understand this one here. So this is a connected universe in the end, right? So unlike this one, we claim, so in this case here, let's go to this. For some reason, that one is connected, but then this one, if we go for the triple case here, it looks so identical to that other one. Okay, graph 3D of that. What the heck is going on here? I don't know what's happening. Well, okay, we can also do let's do the evolution events, whatever it is, plot for this case. What is it called, Max?
Wait, what's what called?
Isn't it events states plots list?
Yeah, events states plots list. Which makes me wonder if you should have the same scene but one generation at a time.
What are you asking? What are you saying?
That would be useful.
And it would be useful to have the one which would just combine every generation.
Yes, to show the event, all events at a particular generation.
Yeah.
So what is this doing? Well, for some reason, this doesn't get stuck. All right, are we going to keep going for a little bit? I'll be right back. Sorry, guys. Keep everybody entertained, guys. I'll be right back.
Is Stephen going to speed eat or? Is he going to come back chewing?
It's possible that either of those may happen. But Jonathan, you could probably take a look at some of the Twitch chat questions.
Okay, yeah, let's do it. Black hole refrigerator to keep your dinner cold from Salon Hugh. Well, the universe invented microwaves. Yep, okay, all good points. I must have, how many people were involved in coding this framework? So it's mostly Max, right? The set replace framework was entirely developed by Max. And then all of the other functionality was developed jointly with between Max, myself, and Stephen, I think.
Yeah, up to the point that we had Wolfram Model function repository, it was mostly me. But now we have some other contributions to set replace.
Right,
mostly with optimizing C++ code. Right.
But then then there were a bunch of the multi-way system framework and all the helper functions and all of that, and that's all collaborative. Could you imagine in 10 years a 5th grade science fair, a kid who wants to looked into this physics project has a library of black hole structures for their project? That is going to be fun. These would be excellent for like science fair projects because they're very visually appealing. It looks like part of a Penrose diagram horizon boundary. Yes, it does. The previous thing that we showed definitely does look like a Penrose diagram for some kind of, well, for a black hole, but not for an event, not for a cosmic event horizon. Okay, here are a lot of memory leak suggestions. Cosmic censorship, Threadripper, people throwing shade on parallel map monitored, which, yeah. How does the cosmological event horizons and black hole graphs differ? Okay, so yeah, we've mentioned this a couple of times. So the cosmological case shows up as a complete disconnection in the causal graph. The black hole case shows up as basically monotonic directions for causal edges. So if you have a region of the causal graph where there are causal edges going in but not coming out, that's the black hole case. So they're both versions of causal disconnection. But kind of the cosmic case is somehow stronger than the black hole case. And as Max says, this is effectively the difference between strongly and weakly connected components. How does the apparent cosmic horizon and UNRRA effect fit into this discussion? That is an interesting question. So the UNRRA effect, okay, for those of you who don't know, is basically, it's the analog of sort of Hawking radiation that occurs in accelerating reference frames. So the idea is kind of, if you are moving very quickly, if you're moving at relativistic velocities, then you will kind of observe, you will observe heat that someone who is in a rest frame would not observe, because as a consequence of your accelerating reference frame, you're effectively producing some kind of apparent horizon, and that apparent horizon will have an effect that's like Hawking radiation. We should be able to see this in our models, right? So once we have and we're planning to do a sort of a live stream reasonably soon about kind of quantum effect. Once we're further along with this black hole stuff, we want to do a live stream about quantum effects around black holes. And in particular, we want to investigate Hawking radiation, which we think emerges when you have disconnections, not just in the space-time causal graph, but in the multi-way causal graph, where suddenly you can have branch pairs which are no longer causally connected. And so one element of the branch pair can effectively escape from the black hole. And we think that's the analog of Hawking radiation. And if that's correct, we should be able to see the analog of the UNRRA effect, because effectively, if you slice the multi-way causal graph at a particularly steep angle, you will also be able to have branch pairs which exist on one side of the slice, but a branch pair at the slice where one element exists on one side of the slice and another element exists on the other side. And that would be sort of the analog of the UNRRA effect. And we're looking forward to seeing things like that. That's a great question. How many orders of magnitude above the causal graph do you need to be to see an electron? This is a good question, and one probably for Stephen. I think he was talking, Max, do you remember the estimates Stephen came up with for electron sizes? They were huge. I mean, we're talking like 10 to the, I don't even know, 50 plus nodes. I can't even remember. Do you?
Yeah, I don't really remember.
It's a lot, but those estimates they're in Stephen's tech paper, but they were achieved by very crude dimensional analysis techniques that I'm not sure any of us completely believe. So the answer is we don't know, but we have reason to suspect that it's a lot of nodes. That effectively the underlying hypergraph dynamics are occurring at a much smaller length scale than anything like we conventionally see in particle physics.
Here I'm back with partially eaten. I have more food to eat, but
perfect.
I was somebody was asking about electron size. I think it's about 10 to the 30th nodes was a.
Was it 10 to the 30th? Okay.
But and by the way, you're talking about branch pairs, and what we're looking at here is space-time causal graphs, and it will be really. I mean, what we were hoping to do is be able to see the entanglement horizon as well as the space, as well as the causal horizon.
Right.
And I mean, this is because we could actually work out the multi-way causal graph for this very rule, could we not?
Mm-hmm. Yep.
I mean, we may be, okay, so we have some slight confusions here about when it has various kinds of, how many black holes. I mean, this rule may not be the simplest one in which to look for a black hole, but this is because it has this nested black hole structure. But just for, we could look at, let's look at the multi-way causal graph for this rule, for this case, right? So that's the ordinary causal graph. Should we look at a simpler one with a sort of simpler black hole? Let's pick a, what's your favorite simplest black hole? I think the simplest black hole we have here, what about this guy here? That looks like a minimal black hole case. Do you agree?
Sure.
Well, I mean, that's what we should see. So let's look at, we think this is a minimal black hole. So let's go down here. So because, I mean, what we really want to see is this thing. Okay, so now let's get the causal graph. Gosh, I'm doing a lot of scrolling here. Okay. So the causal graph for this should show sort of the rest of the universe and then the piece that is the black hole piece. Oh, wow, that's complicated. For something that had that simple of a causal connection graph, gosh. Okay, so let's try to understand the causal connection graph for this thing, just to check that we're not making a mistake there.
Oh, the piece on the left seems to be a black hole.
Okay, hold on. Why are you saying that? Let's see. Oh, because it has, this is cool. Has a bunch of stuff flowing into that, but not flowing out, is what you're claiming.
Right.
Okay, so let's take this rule and.
Yeah, that's actually really neat.
Okay, so let's go 7 steps, 25. So that only got, that was the universe on its own, so to speak. So here, let's try going 10 steps. This is a bit suspicious. Did I get the wrong rule? No.
What about 4 to 15? Maybe it connects afterwards.
Yeah.
Well, what was what was
10?
the parameter value that we used before? Was it 5 to 10?
There we go.
Whew.
Yeah. So let's see if that. So if we do 5 to 15, does it reconnect?
Actually, if you look at it, you can see that it does reconnect because there is one. Although actually, no, never mind.
There's a thing at the bottom where it looks like it might reconnect, but I can't see which direction the arrows are going in.
No, it still goes to the left.
Does it? Okay.
Well, I think we have a black hole there, formed at time step 5.
Yeah, but why it disappears after that? Can you check at which step does it disappear?
Yeah, so what's the interpretation of the thing then disappears by step, let's try step 6. Yeah, I don't understand that. What does that mean? So at step 5, there's a part of the universe that has only a one-way causal connection to another part of the universe. But later, that's not what's going on. explain. Okay, shall I indicate where step 5 is on this?
That would be very useful. Yep.
All right, so let's take this layered causal graph. Let's call it.
Step 5 only has 2 vertices in it.
Okay, how do we get to step 5? We say out component, vertex out component. What should we do here?
No, not really.
Okay, what should we do to get to step 5? It's a layered causal graph, so it should be the case that this thing.
Okay, I'll have to look it up. No, you have to use properties to the Wolfram model. It's not that trivial.
Sorry, can you show me the
Check
causal
which
graph again?
ones.
Yeah.
The big.
It isn't layered in that 5. It doesn't mean actually layer 5. I mean, it's like 1, 2, 3, 4, 5 down here.
Yeah, hang on. There is. Am I misreading that arrow? The thing I was indicating earlier. That is an edge coming out.
From what to what?
From the interior to the exterior. Can I see it bigger, please?
But that's not the exterior, because you can just include this vertex to the interior as well. If you're talking on the bottommost layer.
Well, it's on the penultimate layer. On the penultimate layer on the left, there's an edge coming out.
To where?
To the exterior of the black hole.
I don't think it's. Why do you think it's exterior? Well, maybe it is. Can you plot actually 16 layers instead of 15?
I think that's an outgoing connection. Yeah.
Which means what?
It reconnects. So it's only an apparent horizon, which, fair enough.
Well, so this is, okay.
But it still doesn't explain why it appears at level 4. Or 5.
Okay, well, so anyway, this one is not a convincing black hole. So let's go back and
No,
look
but
at
it's a good example of an apparent horizon.
you know, horizon that survives for a certain amount of time.
Right.
Well, so that is interesting. I mean, clearly what we imagine with Hawking radiation is that, is this what we expect is going to look like when we have Hawking radiation? Or are we going to, in other words, if we project the multi-way causal graph into some particular, updating order, isn't this what we would expect to see happen?
Well, yeah.
So there may be a different updating order. I mean, I think this is not a clean enough black hole that it's worth looking at the multi-way graph for this. What do you think? I think it's going to be a mess. I think it's going to be hard to understand. I think we should pick a simpler case.
We can just see it anyway, just for fun.
I agree that it's a temporary black hole, but it is there for a different reason than we think, because at the level 5, it doesn't appear yet. And it already disappears by level 20. So the 2 vertex graph you see there, it's not because of this black hole, because something else.
I don't understand what you're saying. You're saying that
if you look at level 5, it's too early. This black hole didn't form yet at that level.
Yes.
So it's something else going on.
What's wrong with that? I mean, black holes don't instantly form at the beginning of the universe. I mean, they're black holes. The universe might be born with some black holes.
Yeah, but we are computing it at level 5. And we will get in a 2 vertex graph.
Oh, you're saying it hasn't formed by level 5?
Yeah,
I don't know how you can
but we
tell
are
that.
still getting it.
I don't understand how you can tell that. It depends on the future light cones of all those pieces. But, okay, but let's go back. Okay, you want to compute the multi-way causal graph. Let's go ahead and do that.
Well, because you can go to this black hole from both vertices in level 5. You can just check that. Yeah, if you go to level 5.
Yeah. Level 5
here. Literally level 5 in
4,
here.
5. Yeah. Those two.
Yeah. You can go to black hole on the left from both of them.
I don't see that. Oh, you mean through?
Well, just go down and then keep going left as much as you can.
Yeah, that one does seem to go there. I mean, it seems to go down through this. This is confusing and probably should be checked. But let's just take a look, just to get a comparison of what happens in the multi-way system.
Can you go to 20 levels and see if there's another black hole somewhere?
All right. It's going to get very big at level 20. Let's go to level 20. Can I use oops, level 20. Let me use an aspect ratio here. Oh, can you understand that?
Not particularly.
Good, because I can't either. So, okay, let's look at the multi-way system just for a moment. All right, so we got this. Jonathan, can I say Wolfram Model arrow this? Is that correct?
Yep.
Okay.
That should be in a list.
What?
That should be in a list.
This one here.
Well, actually both, but yes. No. I mean, the rule should be, because otherwise it doesn't know which thing the arrow is applying to. There's an arrow precedence.
Okay.
Ambiguity.
Okay, 2 steps, and then we say states graph, right?
Okay.
States graph structure. Yes. Okay, that wasn't very exciting.
The ever thrilling.
What the heck does that mean?
Oh, that's only 3 events.
Right. I mean, this looks like a fairly standard multi-way system. Can we see the causal graph?
Oh, I see. This is the multi-way system. Let's go to 5 steps.
That's already.
It might even have some causal invariance to it, but let's. Okay, so you're saying causal graph structure, and then I want to see the branchial graph. Okay, can you read that? I mean,
no.
Okay, let's look at the branchial graph.
But actually, actually, look to the left of that causal graph.
Yeah.
That looks like the H event horizon.
You mean where it's going? So if I look at this causal graph, and I make a simple graph here, which is not necessarily, well, actually, if we do look at causal graph instances, that will show us the complete. Well, you're saying there are things that go into that side.
I mean, okay.
I think we really need more steps than this, because last layer will always be a black hole.
No, right.
Okay, now notice the branchial graph here, which has...
Why are we plotting the branchial graph?
Why are we looking at it?
Yeah.
Well, it has disconnected pieces. If there's an entanglement horizon, it better show up in the branchial graph.
Yeah, sure. But we can see that there's an entanglement horizon because there's that.
Where can we see the entanglement horizon?
In the multi-way, in the states plot thing.
Because of this coming off there.
Right.
Right.
Yeah. Can we see a few more steps in the causal graph?
Potentially. I think it's very dangerous. How many more would you like? I'm going to go.
No, let's try. Oh my god.
Well, maybe 6 would have been safer. But what we're getting here, I mean, look, the main point here, again, I think this is a fairly complicated example, and I think we should look for some simpler examples which are more kind of minimalist. But I think one of the things that is, an important kind of meta point is kind of the notion of just a simple black hole horizon. We're going to see a lot more exotic stuff happening here. And, a simple black hole horizon is probably not going to be sort of the whole story. Again, what do you think is going to happen in the case of Hawking radiation? There will be some slices of the multi-way causal graph that should reconnect, right? There'll be causal, because there exist. Do you get what I'm saying? In other words, the fact that there's supposed to be causal disconnection, probably what will be seen is causal disconnection on a certain, okay, there we go. Okay, what would you like to see about this? Well, let's make this layered at least. Well, it's interesting.
Can we do simple graph?
Yeah.
Wait, no, that's a plot. Do simple graph of %69.
Not very. We don't yet know how to read these things.
Wait, hang on. But those two things on the left, those terminate. Those events don't connect to the rest of the system.
Actually, terminate. They might just be the last layer.
Yeah, I agree. I don't think we know how to read these yet. I think we should look back.
Well, we can easily find out, right? We can just include step numbers and then layer it. I'm not convinced. That's the same combinatorial structure that we saw above for 5 time steps, and it hasn't changed. So I suspect that's
right, how do we get the
You see what I mean, right?
Yeah.
Look, that structure on the left looks the same as the structure on the left for the 5-step case. It doesn't look as though it's evolved.
Okay, let's look at the 6-step case, and we'll include step numbers. How do we do that?
Include step numbers gets to true.
And then how do I do the rendering?
Oh, hang on. Did I forget what it's actually called? Does it include step number?
Seems to be happier. Okay. What's that telling us?
Well, so now so it's now layered by step number. So it's become harder to read.
Yeah, well, a simple graph may be easier. And who knows whether it flipped itself around and so on. There's some vague evidence that there's flow in this direction that isn't being, that doesn't have a backflow. But I'm not sure if that's correct. Let's just, for comparison, I just want to look at something with a cosmological event horizon.
That should be easier to spot.
Okay, what would you like to pick? Should we pick the one with how many sub-universes do you want?
Well, if we pick 4, that should at least be easy to identify. But I don't know.
All right, fine. And maybe then these ones here would be interesting. The 2 black hole cases also interesting.
Right. But I agree. I think, yeah. Okay. This has basically convinced me that I need to get my act together on implementing the space-like and branch-like separated highlighting for multi-way system, because it occurs to me in the black hole case, it's impossible to know, right? Because there could be branch-like causal edges coming out of the causal horizon.
Yes.
So yeah.
Right, and that's the interesting case, because that's the case where we can see quantum information basically flowing differently from the causal edges and so on.
Exactly. Right.
And then we want to see the comparison of the branch yield graph up. Oh, that was 16 steps already. Okay. So that is...
oh yeah, look, those are disconnections. Are they?
Yes, yes, they're disconnections. This is a fractal, this is a weird fractaloid universe.
Yeah.
So we should be able to see that. Let's see. Okay, so yeah, these pieces are all disconnected. So this is a fractal universe. I wonder what its spatial graph looks like. And then I want to see the case for the two black holes in the let's see, let's go. States, plots, list, right? See how trivial or not this is. It can't be that. Oh. Oh, well, that's why, because it is.
It's a fractal.
Well, that's why it's a fractal. It's because the actual universe breaks up.
Yeah, that's the most extreme case of a cosmic horizon. There are multiple spaces.
Right. So we probably will see, I mean, arguably up here, wherever it was, here, we should just pick out, well, let's look at this. Let's just look at this two black hole case. And I unfortunately really have to go soon because I've got another meeting at 8 my time. And Jonathan is to be commended because what time is it for you?
It's almost 1 a.m.
Oh, well.
We've done worse.
Yes, we've done much worse. Okay, so this one is a two black holes question mark.
By the way, can we not see the multi-way causal graph for this case? I thought that was what we were.
Oh, for the cosmological case.
Yeah, because I want to see if, because I reckon that's going to be easier to identify.
Yeah, so I think it's going to be lots of identical pieces. I mean, we'll see. Okay, so
what do you mean? No, I want to see whether whether we actually observe this point about disconnection in the causal graph implies disconnection in the multi-way.
This is claimed to be two black holes. This is something which says it goes. There's an initial.
Oh yeah, look. So they're like initially black hole event horizons, but they become cosmological ones because if you look, there are two events going in to the right and two events going into the left.
Yes.
So it behaves for at least 2 steps or 3 steps. It behaves. 3 steps. It behaves like a black hole event horizon, and then it just becomes a cosmic one.
I'm telling you, there's a lot more variety in these horizons, which is why space tunnels might be a thing. Because there's more variety to the weird kinds of singularities that you can get in, in these kinds of models than there is in traditional general relativity. Okay, so this breaks up again. This is again spatially disconnected. Not particularly. So this is, this is a deeply cosmological event horizon, so to speak, because the actual structure of space is disconnected, which is something that cannot happen in general relativity. Correct?
Well, I mean, you can formulate things that have, that are disjoint unions of space-like hypersets.
I understand on manifolds. If you build the manifold that way with the topology that way, but it can't spontaneously happen. I mean, the manifold is stuck with whatever the manifold is, I think.
Right.
Okay.
Can we see the multi-way event, the multi-way causal? Yeah.
Yep. For this cosmological. Let's not live that dangerously. Let's just do 3 there. Okay. I'm convinced we can do 6. Maybe. Wake up. I thought we could do 6.
This is a strong argument for the local multi-way system.
Wow. We were doing 3 before, right?
Right.
Up, there we go.
Oh my gosh.
Okay, interpret. So I think the fact that there are so many, I mean, these are basically, I mean, this is just events that happen separately in different spatial graph components, I think. The fact that there are many parallel lines here is just the fact that things can happen independently in each component.
Right.
But I don't know what this is at all.
And it's not disconnecting, or at least after 5 events, it's not disconnecting.
Yeah, I understand. But then...
But who knows what will happen for, I mean...
Well, there's more to understand. I mean, you know, and we didn't even get a chance to look at what I was hoping we would be able to see is something about no hair theorems for black holes, but we haven't had a clean enough black hole to be able to see that. Right, we're seeing causal edges going into the black hole. What we want to be able to see after that is that somehow, well, it's a little unclear to me. I mean, the no hair statement must be that there's a certain number of causal edges in the black hole and that's all it's ever going to get, unless more stuff falls into it, which is almost a trivial statement.
I'm not sure it's quite that, because I mean, the no hair theorem doesn't tell you about what's going on inside. It just says from an external observer, the black hole can only have a certain class of parameters associated with it. So it's more a statement of, you know, microstates that have gone past the causal horizon are inaccessible to the outside, which is trivially true because that's the definition we're using. But it is somehow stating that there are still features of what's on the interior that we can infer from the external bulk geometry of the causal graph. So in particular, things like angular momentum, you know, our angular momentum construction should still be possible, even though the associated microstates are inaccessible.
But I mean, when the causal graph, it's hard to know how we detect things because we've got causal edges going into the black hole. How do we detect things? How do we detect the properties of the black hole? Look, in the physical case, we would expect that the structure of the spatial graph would be affected by the presence of the black hole because the black hole has lots of T mu nu associated with it.
Right.
And the point is that its effect on the outside of the spatial graph is only as a result of the integral of its T mu nu, so to speak, not the distribution and so on. That would be the claim. So we should be able to see that in, you know, once we can identify a black hole, we should be able to see that in the, you know, in the structure of the spatial graph and in the structure of geodesic balls near the black hole. Yeah,
that's what I'm saying, that there should be features of the bulk, you know, combinatorial properties of the causal graph that allow you to infer certain things about the other side of the event horizon, even though there are no outgoing causal edges.
Right. I unfortunately have to go to something else. This has been good as usual. Sorry, a bit of a cliffhanger. No, it's not really a cliffhanger. You know, it's a cliffhanger would be. I'm going to make a ridiculous joke. I mean, a cliffhanger is like you're hanging on the side of a cliff. At this point, we have a much more dramatic thing, which is the event horizon, and the question is, you know. It's where there are tidal forces as well as just the straight force of gravity. Anyway, never mind. It didn't quite work. All right. Well, all right. To be continued. I think tomorrow we are going to look at. I have just look. Oh, tomorrow we're going to look at Bell's inequalities again, and
Properly this time.
yeah. Well, this time we're really going to focus on Bell's inequalities. I think we're yeah. And well, great. Well, thanks to everybody for joining us on the live stream, and more about black holes soon. So see you all later, and see you, Jonathan and Max and Jose and so on. Okay, bye-bye.